architecture and temperature. Finally, I'll conclude my talk. Quantum mechanics and general relativity are the two pillars of modern physics, but they are fundamentally incompatible. This apparent contradiction leads to the surprising result and effect. It suggests that an accelerating observer sees a vacuum as thermal mass. If we could observe it experimentally, it would not only support these theoretical ideas, but also offer new insight into the nature of space-time itself. However, there is a major challenge. To observe 1 Kelvin under temperature, an acceleration of about 10 to the 20 meter per second square is required, which is beyond our current technology. This motivates us to explore an alternative approach, such as using a circular motion. In uniform circular motion, the proper acceleration is given by this expression. So if we can create a fast detector moving on a small ring, the resulting under temperature becomes large enough to observe. Superconducting circuits are a promising candidate for this. We can fabricate micro-sized rings. Also, in these circuits, electromagnetic wave propagate much smaller than the speed, much slower than in a vacuum. So it's easier to reach a relativistic speed. In our proposal, but punched fluxon-antifluxon pair is in circular motion within the coupled annular Josephson junction acts as a detector. The key idea for detecting the temperature is to use the relative motion of the detector. Let us now explain the system in the more detail. Starting with the single Josephson junction, where an insulator is sandwiched by the two superconducting layers. Here, Maxwell equation is written like this. Applying the Josephson relation like this, we can express the current, electric field, magnetic field in terms of the phase difference between the superconducting wave function of the in the either side of the junction. Combining these results leading to the sine-Gordon fluxon. Since the magnetic field is proportional to the spatial derivative of the phase difference, the fluxon carries a localized magnetic flux. The direction of the fluxon depends on the sign of the kink. We call them fluxon and antifluxon. Physically, the magnetic flux arises from a circulating current across the junction and propagates along the transmission line at a constant velocity. Our model consists of the two stacked Josephson junctions connected to end like this. We define the radial direction of the ring as x-axis. Assuming the ring is large compared to the fluxon width, the dynamics can be approximated at experimental condition, we evaluated the White-Band function at the laboratory temperature following the previous works. This leads to the frequency-dependent effective temperature, which captures the non-equilibrium nature of the circular motion. In the low frequency limit, we obtain the constant effective temperature like this, where the gamma zero is a constant defined by the integral of White-Band function. This figure shows the control plot of the effective temperature using the feasible parameters. The effective temperature reaches a few Kelvin, showing the feasibility of the detection. In the low laboratory temperature and relativistic limits, the integral gamma zero can be analytically calculated, and we obtain the well-known under temperature expression. The laboratory temperature slightly raises the effective temperature, but under cryogenic conditions, it is still much lower than the under temperature. So the dominant effect here comes from the under effect. Here, I explain how to measure the under temperature. The key is the reactive motion of the fluxen pair, and we use a switching current distribution to measure the temperature. The relative motion can be seen as a motion in the motion of the virtual particle in the potential. The nonlinear term creates a potential wave, and the bias tilts the potential. By increasing I1 while decreasing I2 at the same sweep rate, we can keep the sum current constant and increase the relative current. When I minus equals 0, the virtual particle is trapped in the potential, oscillating back and forth. Since RR represents a distance between the fluxen and antifluxen, this corresponds to a band-to pair vibrating. As I minus increases, the potential tilts and the barrier lowers. At the critical point, the barrier vanishes, allowing the virtual particle to escape. This means the pair breaks apart. We can confirm this collapse as a transition to the voltage state. By measuring the voltage change, we can determine the switching current. Now let us consider the effect of the temperature. At the temperature, there are no thermal fluctuation, no fluctuation, and the transition to voltage state occurs at the same current in every trial. On the other hand, at the finite temperature, thermal fluctuation cause the virtual particle to escape even in the potential well. As a result, the transition to voltage state becomes distributed, with the switching current varying from trial to trial. As the temperature increases, the distribution shifts to the lower current values due to the larger fluctuations. We numerically simulated the Langevin equation with Gaussian noise 10,000 times. Colored bar represents the result of the numerical simulation. The solid line represents an analytical solution derived by the Arrhenius formula, and it shows a good agreement with the numerical simulations. We show the result for various detector velocity, which indicates the distribution shifts toward lower as the temperature increases. This means that the observed fluctuation comes from the acceleration. In summary, we propose a new method to detect the under effect using an experimentally feasible superconducting system. In this system, fluxon and antifluxon pair formed in the coupled annular Josephson junction act as the detectors undergoing circular acceleration. The effective under temperature is estimated in a few Kelvin, making it observable in experiments. Numerical simulation of the switching current distribution show the acceleration dependent, proving the evidence of the under effect. Thank you very much for your attention. This G represents a Weidmann function. Okay. I didn't say the detail here, but um, I'm considering the Caldera-Leggett model. And I'm assuming the coupling with the environment scalar field with the relative coordinate. Okay, thank you.
Qual è il filo? Ah, eccolo lì. Ok. Sì, sì. Sì, sì, Accademia hai. Grazie. Vai, grazie. Ok. Ah, ok. So, 1 second. Let me just connect this because how do I do this? There is a there is a USB. Okay, so I flip with this. Okay. Anyway, thank you. Yeah. Okay. So thanks for the introduction. Yeah, I'm Francesco. I'm a postdoc at Niels Bohr Institute in Copenhagen. But actually today I'm telling you something that I did like last year when I was finishing my PhD. And as you can see from the title, I will talk about Hawking radiation with a particular technique, which is the tunneling method, and in a particular setting, which is the analog gravity setting. So there are two main ingredients for the results that I am going to show. And the first one is the derivation of Hawking radiation tunneling process, and then I will speak a little bit about analog system in general, just to give a setup, and then I will go through my results. So basically, Hawking radiation is a tunneling process. This is one of the many derivations that you can give of Hawking radiation. Here you can see like a very simple case. So Hawking radiation is a quantum field theory curve spacetime effect. So here we have our curve spacetime, which is just Schwarzschild in Eddington-Finkelstein coordinate. There in the picture are depicted the outgoing geodesics, null geodesics, and the ingoing one. You put your quantum field on top of it. So your Klein-Gordon massless scalar field, for in this example. You solve for the Klein-Gordon equation, and near the horizon, the set of the outgoing modes look this way. So it's basically it's a field with a shape of an exponential with some phase, and this phase presents a non-analyticity at the Killing horizon, which basically, in a particle interpretation of this kind of field, tells you that there is no, let's say, outgoing radiation which classically can cross the horizon this way, and there is no classical, let's say, trajectory who does so, but there is a semi-classical trajectory who does so, in the sense that in the 1999, Parikh and Wilczek showed that the thermal properties of the horizon can be computed as a quantum tunnel out of this particle following this classical orange path, then tunneling out semi-classically, and then arriving to infinity with the classical allowed outgoing trajectory. And in order to evaluate so, it's very simple, it's very intuitive, because you just need to complexify your path for the point particle trajectory, and you take basically the residue of the integrand, and what you get is the tunneling rate, which is given by this formula. And the tunneling rate in this case appears to be a Boltzmann factor, where omega is the energy of the mode of the particle emitted, and T is the Hawking temperature. This can be easily connected with the Bogolyubov calculation, and this basically tells you that at infinity, if you're sitting down, the black hole emits particles with a thermal rate given by this temperature here. Second ingredient, analog spacetimes. Most of you know what I'm going to talk about. Analog spacetime is just the idea that if you take a fluid and you linearize its constitutional equation, basically what you get is that the background describes for you curve spacetime. So you can, let's say, bring your curve spacetime in your lab, and the phonons will be given by equation of motion as fields in curve spacetime. In this case, a Klein-Gordon field in curve spacetime. That's super interesting because it's something that you can actually do in your sink, and basically you can create black holes. That's the interesting part, and that's what I'm going to talk about. So this is 1 + 1 dimension of an analog metric, where Cs is the speed of sound that the fluid propagates with, and V is the velocity of the background stream, of the background flow. Now, let's imagine this is 1 + 1 dimensional. So let's imagine that you, at some point, the background velocity overcomes the speed of sound for a phonon. Then no matters the excitation where it wants to travel, it will be dragged by the stream itself. So this is a concept of a sonic black hole. It's very easy, and exactly the horizon is given exactly from the equation that the speed of sound has to equate to the background fluid. Okay, this is a very nice idea, and it's super nice because you can do quantum field theory in curve spacetime on that. The thing is like that not all the fluids are suitable for doing quantum field theory in curve spacetime. Here I have an example of a suitable fluid for doing that, which is a Bose-Einstein condensate, which do the job for you in the sense that you can still play the same game. You can linearize the equation of motion, playing like mean field approximation plus perturbation. You can quantize this perturbation, so you can actually test semi-classical effect. But usually, this kind of fields, the important part, I put a slide just to show that this kind of fields enjoy a modified special relation usually. Depending on the fluid you're working with, you almost never are relativistic. At some point, with some cutoff provided by the system that you're working with, your dispersion has been modified. In this case, it's superluminal, supersonic, superluminal, as you want to say. It can be subluminal, or it can be also subluminal, depends what you're working with. So people have looked at this problem, but just let me sketch you how things change when you start from the relativistic case, here there is the fluid velocity, here there is the time, laboratory time. Basically, the trajectory of the particles are the same, but when you modify the dispersion relation, where this psi basically depends, is a plus or minus 1, depending whether your modification is super or subluminal, basically you obtain different trajectory for the particles. And in particular, what I want to stress is that what was the characteristic peel out of the outgoing trajectory from the horizon of the Hawking quanta, now it's modified very, very drastically. So you can ask yourself if there is Hawking radiation in this kind of system, and the answer, I mean, I'm here talking about Hawking radiation, so the answer is yes. And at least this is the case when lambda is very, very high, right? So if you turn off this modification, you expect to recover the relativistic result. And this has been also provided experimentally. There are many theoretical works behind that. And the thing that you can actually probe this, because you can access to the Hawking quanta and its partner inside the black hole, because you're not dealing with a true black hole, you're dealing with an acoustic black hole, so you can measure the correlation between these two and evaluate, let's say, the Bogoliubov coefficient, and so the fact that the pair production happens with a thermal rate. Now, what I want to show you is that with the tunneling, we can recover the same effect. So it's the first time someone has applied this technique to this kind of settings, and we can get even more, because we would like to go beyond the zeroth order where lambda is infinity and take, let's say, into account correction. So basically, the situation is the following. We have this complicated stuff, but this is the subluminal case, this is the superluminal case. But what you really care about, or at least what experimentally they detected, is just the correlation between these two upper branches. So the guy who happens to escape at infinity, and the other particle, the counterpart, the negative energy falling into the black hole, extracting energy from it. So that's basically what we care about. And it seems not to care that much, that we don't care that much at what's happening here below. I will be clear in a minute. So in trying to understand this with the tunneling method, we cheated a little bit, because we said, okay, let's just focus on these two branches that I highlighted. So this is the superluminal case, for example. So if you focus on the Hawking quanta very far from the black hole, you see that basically this trajectory is given by the solution which is ingoing, just flipping the sign of the velocity. This is pretty intuitive, but it's also in the relativistic case. You just flip the direction and you get an outgoing trajectory. Quite interestingly, the same happens for the Hawking partner, which is inside. Now it's cut, but you see there is an ingoing mode, and then you flip the sign and you jump up here. Okay. Let me just underline that all these behaviors depend on the energy of the particle, because this is not relativistic, this doesn't follow geodesics and anything. But at least you know that if you take this blue trajectory, you flip the sign, you get a well description of the two branches of the solution that you're interested in. That plays the role of the Hawking partners. So the situation is the following. If you actually take your ingoing mode and you flip the sign, you get this blue dashed line, which does exactly what I was describing. Basically, it well describes the branches which take place to be the ones that you measure the correlation about, and it deviates strongly from the behavior of the real trajectory near the horizon. And this horizon here, we called it effective horizon, because it's not anymore the killing horizon. It's just an effective horizon that the particle with the given energy feels like, and it respects the same equation that the relativistic horizon respects with the speed of sound. So you have basically the picture is the following. You have particle moving with different energy, and at each energy to corresponds a position of an horizon, we see is exactly where this approximate with blue dashed line, the minus ingoing ray, peels out. So if you pretend this to be true, we can actually do a lot, because we can use the tunneling now. We can compute the tunnel out at the effective horizon, and we can extract the temperature, the rate of production of this particle. the rate of production, which happens to be, again, a Boltzmann factor, but with a temperature which is not a temperature, because the emission is non-thermal, since the special relation is modified, and particle moves not universally, but depending on their energy. But actually, with this method, we are able to compute analytically the correction of the spectrum with respect to the leading order, which is just the Hawking temperature. When alpha is just the ratio between the energy of the particle, the quanta, over the cutoff of the theory. And actually, no one stops you to go, let's say, to push it further and to get the following picture. Subluminal horizon, which is like a little bit bigger than the relativistic horizon, because particles are slower. Superluminal, you access a little bit the region inside the relativistic horizon, and the position of your effective horizon is inside. This is actually the picture that I was telling you. So this is in the subluminal case. It's interesting that the horizons stay outside, because it tells you, this is my last thing, but just it tells you that you don't need actually an analog black hole to undergo some kind of Hawking radiation. You can have particle production for horizonless object, actually. And that's what we also computed, because if you take a stream which goes almost, let's say, to form an horizon, but so it's an analogous of a very compact object, but it doesn't form really an horizon, still this calculation gives you that there is some particle production, which is highly suppressed with respect to the leading order that would be in the Hawking case, but it actually answers some question that is posed in the literature, like regarding the subluminal dispersion relation. Just one word, which I think is the most interesting point, about why we should trust this calculation and why this works. Because basically, I said to you that I am applying a calculation here very close to the horizon, where actually my approximation fails to describe the trajectory that I'm describing. But if you, let's say, go back to the heuristic interpretation of Hawking radiation, basically you have two particles creating from the horizon and then departing and going up to infinity. But you cannot talk about two particles if they are too close. If two particles are within a single Compton wavelength, they are not two particles. It's just a quantum cloud of stuff. So if your approximation describes your trajectory within this, when this equation is respected, then you're fine. And what we find indeed is that this is a good approximation, no matter the flow for alpha going to zero, so for very low energy with respect to your cutoff, and which connects with the relativistic limit. And then it's a good approximation whenever the flow is steep, because everything is concentrated in a very, very small, let's say, delta x. So, and this was also observed that local physics shouldn't affect Hawking radiation in this kind of, in previous literature. So, just concluding, we saw that Hawking radiation is robust under modification of the special relation. And actually, we can describe with the tunneling method in a very simple manner, and we can do more going beyond the very complicated and numerical Bogoliubov calculation that people have done previously in the literature. And this allows us for free to understand why horizonless object should undergo some particle production phenomenon. And given that, thank you, and sorry going over time. The When you subtract the, you mean in the original paper? Okay, no. Uh-huh. Yes, absolutely. I didn't know about this paper, but yes, please send me the, yeah, thank you.
Good. Yeah, sorry for the changing the title of live there. Oh, so yeah, thank you for having me. I mean, slightly changing the title because I'm going to talk about analog gravity. We in Nottingham are a mixed experimental theoretical group which work on exploiting all the analogy that you and Francesco talked about between fluid dynamics and QFT to observe some of the interesting phenomena in the lab. But I want to even to pursue some of a slightly different point of view that differs from the very beginning of the foundation of the field. There was more developing some experiment in so very narrow region of parameter space where this effect can be studied and this mapping with Klein-Gordon propagation is exact. I want to present you the motivation why even where you are, beyond or outside this regional parameter space, you can still have a lot of interesting physics. There are a lot of experiments down out here with some very intricate and complicated dynamics that we can look at through the lenses of analog gravity. And in exchange, we get new physics, very important physics that we can look at. So the subject of the talk are quasi-normal modes. And quasi-normal modes are, in a nutshell, resonances of dissipative systems. Dissipation can come from, coupling with an external bath. Think of a harmonic oscillator just coupled with some friction, or it can come from very peculiar boundary condition. In the case of a black hole, what you get is like that when a black hole gets perturbed, it will emit all the gravitational wave toward infinity. So you have an open boundary condition on that side, but even toward the horizon. Sorry. So these boundary conditions selects a discrete set of modes characterized by complex frequencies, so they decay in time. And the importance rely on the fact that the collection of these resonances, the quasi-normal spectrum, is just a fingerprint of the resonant object. And since this is one of the few things that you can observe in gravitational wave physics, this is why there's a lot of efforts in understanding how this quasi-normal mode spectrum changes when you change theory and how to properly characterize the object. From a just mathematical standpoint, most of the equations that when quasi-normal modes are concerned are just at the linear perturbation level. So you have a kind of wave equation with a potential. You can formulate a scattering problem, and the complex poles of the relative transmission and reflection coefficients will tell you where these quasi-normal modes are, because are modes that satisfy these outgoing or radiative boundary conditions. But as I said, the quasi-normal modes and ring down is one of the most important observables, and there is a lot of effort to understand how, for example, the quasi-normal mode spectrum could be used to detect deviation from GR. But unfortunately, it's very hard to probe all this beyond GR physics numerically. Numerical relativities keep on struggling with the hard modification of GR. But fortunately enough, we can use analog gravity system to do that. I will go fast here since Francesco just give a good introduction of the field. But among the different kind of simulator of analog gravity system that you can use, Francesco presented sound waves. Here we work with surface wave. It is an analog system introduced by Andrew and Schutzold. Basically, the dynamics of surface wave propagating on top of the fluid flow can be mapped to the dynamics of a field on a curved space-time. Given that you are in what is called the shallow water limit, so you're considering very long wavelength waves. And this is because all the nonlinear behavior of fluid dynamics just simplifies. And if you're in this regime, you just get, again, a Klein-Gordon equation. The field has been incredibly successful in observing some of the phenomena like Hawking radiation, super radiance, and so on. not only in gravity waves, but even in other systems. But again, I want to stress that in order to get here, to get this analogy, you need to be very careful in how to design your experiment. And it's pretty hard to be in the condition where this equation actually holds experimentally. Now, I'm going to talk a little bit about this is our experiment. You're going to learn more about it tomorrow in the plenary talk by Singh van Voortner, the head of our group. Basically, this is our vortex flow. It's very hard to see. This is the trove. It's like the most transparent substance in nature. So yeah, it's quite hard to see. This is superfluid helium at 1.6 Kelvin. And these small ripples they may be able to see are our observables. And you can clearly see that this is not the shallow water regime. The waves are very tiny. The depth of the fluid is massive. And is not infinite. I tell you about the wave propagating up to infinity before. Clearly, this is not the case. But again, let me just reiterate this. The original gravity formulation just rely on a lot of hypotheses that you need to put into your modeling. But I mean, there's so much more out there than Klein-Gordon equation. I mean, and in particular, our system naturally probe another portion of the parameter space when dispersion can't be neglected. We're still having this low viscosity limit, but still we have a massive presence of dissipation. And it's not that, again, the point of view that I want to convey is not that this is just a bad simulator. It's just simulating something else. And in particular, what we're simulating is propagation of a field in a Lorentz breaking theory. And it's not something, out of this world. If you try to go beyond GR in many effective way, you're gonna end up with this kind of terms. And so, yeah, what we're actually simulating is something different. Now, a little bit on the technical part. When we have dispersion, this means we deal with a wave equation like the first one. dt is just a material derivative. F is what is called the dispersive function. It only depends on the spatial derivative, so you can see why it breaks Lorentz symmetry. And yeah, the dispersion relation then tells you what are the modes that are allowed to propagate in your system and their propagation speed. Yeah, they are kind of complicated system to study. What we do is to rely on what is in gravity is known as WKB approach, more general in the ray tracing techniques when you deal with highly dispersive system, which is basically separating the scale. We assume that these waves propagate on a background which varies much slower than the actual wavelength. In this way, we can formulate the dynamics of wavefront, so collection of waves with the same phase, in terms of an effective Hamiltonian system. And once you have an Hamiltonian, you can study, for example, classical turning points. In this picture, it would mean that you have a front wave, you have a wave that propagates. At a certain point, it encounters this turning point, it just gets reflected back, as if there were a effective potential, a repulsive potential. And yeah, in our case, since we deal with stationary azimuthal axisymmetric systems, we just can decompose and look at each single modes. And what we have is something like this. So here, I plotted the effective potential experienced by waves that propagate with the vortex and against the vortex. Again, ours is a two-dimensional system, so you have this breaking of the symmetry, as in Kerr black holes, for example, right? When you have all the frame dragging. And for modes that propagate with the flow, you have just that a wave that comes from outside would just see a repulsive barrier, and you will have a lot of standing waves. This is presented in this paper. But the interesting part for us is that for modes that propagate against the flow, the potential has a maximum. Potential as a maximum means you can apply the radiative boundary condition for quasi-normal modes. So these systems can support the presence of quasi-normal modes, as in black hole physics, but with all the information about dispersion encoded in what is called now, what we can extract as the effective reflection coefficient, which will tell us where these quasi-normal modes are. So this is how we take into account dispersion. But again, there is another element that we need to add in our modeling. Every experiment has a finite size, unfortunately. And for this reason, we need to take into account the fact that this purely outgoing boundary condition can be exactly imposed. But there is a huge literature about how quasi-normal modes gets modified when some kind of confinement is introduced. It's called the spectral stability theory. It's a very important study because you want to know if your quasi-normal modes are a reliable probing tool for your system. Because if they get modified by small deviation in your potential, they're just unreliable. So we apply all this machinery of spectral stability theory in our case. We see something like this. These bright spots are the resonances of the system as a reflective wall is introduced, and we increase the reflectivity of this effective boundary. And we see that as the reflectivity increases, you get all these modes translates continuously to other modes with less imaginary part. This means they will stay longer in the system. The decay is lower, means it's easier to detect them. And there's some big advantages. And as a side effect, you have that if you insert another essential feature of any realistic experiment, there is noise. You don't even need to send a wave, as the simulation I showed you before. You just need to probe to measure the noise flow. And the presence of a boundary makes the noise flow modulated such that you can extract the quasi-normal mode from just this noise. So you have basically the quasi-normal mode of your system for free. And this is now some experimental verification. We put all of this together, describing this very messy vortex flow with a lot of things going on. And let me just point out, the dynamics of free surface helium vortex flow is a very timely research topic right now. You can literally count with your fingers the number of numerical simulation they can do that. They can tell you what the shape of the thing is. It's very hard. Then here, thanks to all these machinery, all these concepts that we brought from gravity, we were able to identify among all the mess, those resonances that are related to quasi-normal modes. Here, this is our observables. So we get a video of the surface, we reconstruct it, we decompose it for each in the spectrum of each azimuthal component, means modes with a number of crests as you go around. And we then identify among all of these the observables, which are related to the quasi-normal modes of the open system. And this is how they come from the quasi-normal modes of the open system case. And we did it for a lot of them. Quasi-normal modes are very hard to detect, usually in gravitational systems, because they decay very fast. So it's very hard even to detect all of them. But we managed to detect a lot in different M channels. And so I leave you with a summary. Thank you very much.
Yeah, sure. Oh, Paczos. Sorry. Yeah, sure. So, Thank you for the introduction. Thanks to the organizers for putting this conference together and for the opportunity to give a talk. This will be based on a project I did in collaboration with Navdeep, Sofia, Daniel, and Magda on how gravitational waves affect spontaneous emission. Since they were first predicted in 1916, gravitational waves were mostly studied in terms of their interaction with classical test masses. This is most commonly visualized as follows. Okay. So we imagine a ring of classical test masses and a gravitational wave traveling in a transverse direction. And as the gravitational wave passes by, it squeezes and stretches space in two directions, so that the ring of test masses is deformed as on this picture. This behavior is at heart of most of the detection schemes, including interferometers, levitated masses, or optical atomic clocks. What has gained significantly less attention so far is how gravitational waves affect quantum systems. Nevertheless, it has been shown that when interacting with atoms, gravitational waves can induce small shifts in the internal energy levels or even resonant transitions between them. And the interaction of gravitational waves with quantum fields has also been studied, in particular in terms of particle production and scattering. Now, the goal of our project is to study how gravitational waves affect the interaction between those two. And in particular, we are interested in the process of spontaneous emission. In our model, gravitational wave is a plane wave traveling along the z direction. It has amplitude A and frequency omega, and its only role is to fix the background, to fix the metric. We take a simplified model of the atom, so a point-like two-level system with energy gap omega naught, and we associate to it the monopole operator. For the quantum field, we take a real massless scalar one. We quantize it on a gravitational wave background. That's how the gravitational wave enters the consideration. And we associate to it the field operator. And finally, we consider a standard monopole interaction Hamiltonian with a small coupling constant in front. And note that with this interaction Hamiltonian, the only way in which the gravitational wave enters the interaction is through this field operator. So in particular, there is no direct coupling between the gravitational wave and the atom, which means that we are basically neglecting the energy shifts and the resonant transitions that I mentioned. Okay, now, since we are interested in spontaneous emission, we assume that initially the atom is excited and the field is in its ground state, in the vacuum state, sorry. And moreover, we assume that the atom follows a static trajectory at the coordinate origin, which in the metric that we consider is a geodesic. Now, we look at the state of the system at time t, expanded up to the second order in the perturbation. And given this state, we ask, what is the expected number of photons with momentum k emitted up to this time? And we show that this number generally splits into two terms, a flat space-time contribution, which would be there even in absence of the gravitational wave, and the gravitational wave correction. And we derive the formulas for these two contributions. They are not relevant for now. What is relevant, though, is that both contributions depend differently on the photon momentum. So in particular, if we look at the frequency dependence, here we define the tuning of the photon from the atomic resonance. We have that the flat space-time contribution goes like Singh squared function. So it's a sharply peaked function around delta k equal to 0, which means the exact resonance. On the other hand, the gravitational wave correction is a product of Singh functions with different arguments, and this has more peaks, not only in the middle, but also on the sides. So gravitational wave will give rise to sidebands in the emission spectrum. Next, for the angular dependence, we introduce the spherical coordinates in momentum space. And basically, there is no angular dependence in the flat space-time contribution. The emission is homogeneous. But in the gravitational wave correction, there is some dependence. So gravitational wave will also induce a directionality of the emission. And these are the effects that, at least in principle, we can probe. So we can measure photons emitted with different momenta, and we can tell whether there was a gravitational wave or not. Now, is it possible only in principle, or can we really do it? And if we can detect the gravitational wave in this way, how hard is that? Before I answer this question, let me ask a related one, namely, given that we measure the photons emitted, how well can we estimate the gravitational wave amplitude based on this measurement? To answer this, we refer to estimation theory and the standard result, the Kramer-Rao bound, which tells us that there is some minimal uncertainty. There is a bound on the estimation uncertainty given by this inequality. And here M is the number of independent repetitions of the experiment, and curly I is the Fisher information, which in simple words tells us how much information we can extract from our system with a given measurement. So now assume that we perform an idealized measurement such that we measure the emitted photons for all momenta k, but we resolve all the frequencies and all the angles. So what is the Fisher information in this case? While we do not derive an explicit formula for the Fisher information, we derive a lower and upper bound. Again, the formulas are not relevant for now, but here is the plot. Oh, this looks terrible. Okay, but I guess you can see what's on the plot. So we have two oscillating functions, and there are some specific times at which both bounds coincide. So at these specific times, we can tell what is the Fisher information exactly. And moreover, at this specific times, the measurement that we perform is an optimal measurement. We saturate the so-called quantum Kramer-Rao bound. Okay, so I will call these times the optimal times. And let me go back to the gravitational wave detection. So we have our Kramer-Rao bound, but now let us think of M as the number of atoms that we use. So instead of just a single atom, we take a bunch of atoms and we look at their spontaneous emission. And assuming that, and we say that detection is in principle possible if the minimal uncertainty of estimation is smaller than the gravitational wave amplitude, which gives rise to the following condition that we have to satisfy. And assuming that we probe at these optimal times, this condition can be translated into the minimal number of atoms that we have to use to be able to detect gravitational waves in principle. So if we insert typical numbers, gravitational wave amplitude of the order of 10 to minus 21, omega naught, the optical frequency 10 to 14 hertz, and look at the gravitational wave frequencies corresponding to the lower LIGO bands, so 10 hertz, then it turns out that we need at least 10 to 16 atoms to be able to talk about gravitational wave detection, even in principle. That's a lot, but that's still microscopic. However, lower LIGO limit is not the ultimate limit on the existing gravitational waves. There are gravitational waves with lower frequencies, and what limits our scheme is the line width of the atomic transition that we consider. So we cannot detect gravitational waves with frequencies lower than the line width. And if we look at ultra narrow line width transitions, for example, those employed in optical atomic clocks, then the line width is 10 to minus 3 hertz, and the corresponding required number of atoms is 10 to the 8. This is not much. This is achievable in experiments with cold atoms. Okay, so to sum up, we show that gravitational waves induce sidebands in the emission and directionality. This is an effect that might be detectable. Well, to make precise statements, one would have to look at more realistic model of atom-light interaction, so a dipole coupling to electromagnetic field, and include various noise sources. But, well, it seems that this is an interesting direction to explore. And finally, let me point out once again that the only role of the gravitational wave in this scheme was to fix the background. So we can also consider different spacetimes and employ the same reasoning there. Therefore, can we use spontaneous emission to probe spacetime geometry? Thank you very much. Yes. So when I was showing the upper and lower bounds on the Fisher information, the upper bound is given by the quantum Fisher information. I was not very clear. Yes, that's how we derive the upper bound. No, we have not. We have not done it. Okay, okay. We'll look into this.
Again, between atom gravitational field.
The atom and the gravitational field in our model. no coupling. There's a coupling between quantum field and the gravitational wave, and the atom is coupled to the quantum field.
Okay. I didn't understand that. It's like a main gravity is
Yes, exactly. Yes, yes, yes.
Thank you.
Oh.
Yeah. Okay. Thank you. Yeah. That seemed too quiet. Okay, thank you. And I wanted to start by thanking the organizers for organizing the conference, but also giving me the opportunity to speak. I'm going to be showing some work that is in collaboration with other people from Nottingham listed there, but also one of our external collaborators with their name cut off, unfortunately, Tajik. So the contents of the talk are basically going to be the title in a changed order. So I'll first go through some sort of experimental details. I'm going to tell you a bit about the thin film, the superfluid helium, and the word simulators. Then I'm going to detail the goal. So this is going to be the information. And then the last part is kind of hiding in the title, but I'll tell you about the method of getting it, which is just the word in. So how do you get information in those experimental systems? Starting off easy, I'm going to tell you about helium. So helium's a gas at room temperature. You put it in a balloon, it goes up. Nothing that exciting. If you cool it down, it becomes a liquid. Nice, better. You can use it for some industrial applications like cooling magnets, but still not what we're interested in. Keep going, and below 2 Kelvin, you get to superfluid. And thinking intuitively about the superfluid, it's nice to think about a model proposed by Lev Landau, where you imagine it is one fluid, but you imagine it as two. So imagine that it is made up of a viscous part and a superfluid part. The viscous part has some viscosity, doesn't flow completely freely. The superfluid part doesn't. This is just an imagination. They all form one fluid, but it's helpful to explain the physics of the system if you think about it in those terms. So for example, what are some effects that you can get? You have two components. They can both oscillate. If they oscillate in phase, you're going to get some sort of sound from these oscillations. And when those components oscillate in phase, it's a normal sound that we're used to, which we call first sound. But those components can also oscillate out of phase. And when that happens, you get another type of sound. Now, no longer waves of density, you get waves of pressure for your superfluid. So there's one effect that's easy to think about in terms of two components. Another fun thing that superfluid does is if you just take a normal fluid and you put it in some sort of a container, whatever that container might be, it will form some sort of a slight meniscus. So it will clip onto a boundary. You're used to that with a cup of coffee or something. If you take a superfluid, it doesn't do that. Its minimum energy configuration is to just go everywhere. It coats absolutely everything, and I do mean everything. So I'd kind of try to implicate that with coating the slide, I guess. So this is some of the effects, and like I said in the title, we're going to not be looking at the superfluid itself. We want to look at a film, right? So instead of talking about this bulk things happening in there, let's look at a film. This is not an image of the film. The image of a film like this does not exist. This is a nice schematic representation. If you make it really thin, so under 10 microns or so, and if you make it really cold, so above 1 Kelvin at this point, it becomes pretty extreme. So first of all, the effective gravity that it's feeling on the surface becomes really strong because it's no longer dominated by actual gravity. It's dominated by the van der Waals interaction between the helium atoms near the interface and the substrate that it sits on, which can be really strong. So, for example, you can reach regimes where the effective gravitational force on the interface is comparable to the surface gravity of the sun. So the frequencies and the wavelengths of that superfluid thin film are going to be very different from what you're used to in other fluids. But also, I've told you about these two components. In this case, it's kind of a schematic representation again. The viscous part is stuck. Even at below 1 Kelvin, there's very little of that viscous part to begin with, but whatever is left becomes clamped to the bottom. So the actual interface between the helium superfluid and vapor becomes completely viscosity free. So if you now take some variables to describe that interface, so I'm going to take perturbations in height that I'm calling psi on the interface only, and the velocity potential phi on the interface only. In the long wavelength regime, which we've heard a lot about from previous talks in this fluid analog ideas, you get linear dispersion, which means you get sound. I've also kind of already spoiled what sound it is with that little C3. It's another type of sound. You get third sound. This is now very particular only to those thin films. This third sound only propagates in those, and it's sound that appears as actual height perturbations of the interface, even though it's sound. So it's a strange type of sound. You can quantize it following Lev-Landau's quantization of the superfluid at the interface only now. And last year, from people in our group, it was shown that it follows this Hamiltonian, where rho is the density of your fluid, h naught is the equilibrium height of the film, the perturbations are on top, and the rest I've already said. So kind of the conclusion here is, in some regimes, which in the paper from last year you can is argued are reachable, this thin film interface will behave like some sort of a scalar field. Okay, so we have some type of a simulator if you can reach this regime. So that's the kind of introduction of the theory. So onto the experiment. This is what's this is about 2/3 of what's already built in Nottingham and running. This is the cryostat, so it's cooling down a cell at the bottom, which is that little cylinder, to about 300 millikelvin. That cell, like I said, is a cylinder. Inside the cylinder, you've got superfluid helium at the temperature that I've already mentioned. And at the bottom and at the top, you get a window. You can also see a mirror at the top of that block, so you can actually shine a laser through the thing, reflect it at the top, and watch it from the other side, so you can probe optically the system. So to show you a little schematic, here is the laser passing through the bottom window. The superfluid will pool into little ponds on the side, and the thin film will extend from those pools all around the cylindrical cell, including the window that the laser is passing through, which means that the laser is going to be sampling the height fluctuations of that superfluid thin film, and by doing some interferometry or digital holography, you can reconstruct the height perturbations with spatial resolution and over time. So you have something that in an appropriate regime should behave like a scalar field. You have one of the quadratures, the height perturbations, that you can measure, and you can measure them quite well because you have space and time resolved measurements. So it's looking pretty good as a simulator to begin with. And then you have the question of what do you want to simulate once you have it. And various things come to mind and various things we're working on. But for this, I want to talk to you about information. Again, just following the title along. By that, I mean specifically mutual information. So I'm going to define mutual information I. So this is information between A and B. A and B can be some regions. And it quantifies correlations between A and B of any type, of any order, quantum or classical, just puts them all into one number. So it's a good quantifier of correlations, where S is von Neumann entropy, and you find subsystem by partial tracing. What I want to do is I want to find this mutual information between various A and B. So change their geometries, change their positions, change their volume or the boundary area between them, and see how the information responds in various scenarios. Particularly, an interesting thing that appears is area laws, where you can find states in certain systems where the information doesn't change with the size of the system, it only changes with the size of the boundary between the two. So this is something we want to probe, but in general, this is maybe far too ambitious. We have a general state of any type. It can be very complicated. You have a continuous system that's big, and measuring something like this is just going to be ridiculously hard. So let's simplify a bit. What if we find and this is in process of checking, that the state of those interface variables are Gaussian. That would be nice. If they're Gaussian, you just need first and second moments. For information, actually, you don't even need the first moments, you need the second. So you just look at covariance. You build a covariance matrix. That covariance matrix is made up of quadratures of the field, the conjugate momentum, which for us is the height perturbations, and the mixes, and you can find entropy of the total system. If you have the covariance of the total system, you can also section it in a way that you do a partial traces, but on a Gaussian system, it's easier to find subsystem entropy, and you should be able to find mutual information. I've simplified, but that's still not something that seems possible because we have one quadrature, and for the covariance matrix, you need both. But in that sense, there is some hope. So I'm going to take a small step back. I'm going to imagine some general simulator. So I'm going to have a Hamiltonian of some free theory where phi is the field, eta is the conjugate momentum, and I'm allowing a mass. It might be there, it might not be. Let's put in some volume. Volume can be whatever. Just imagine some sort of a geometry. And let's impose some boundary condition. That boundary condition we've done for Dirichlet, Neumann, and Robin. Everything I say will work for those. Perhaps it works better, perhaps it doesn't, but it definitely works here. Where Robin is a boundary condition that smoothly interpolates between Neumann and Dirichlet. The reason we do it for a lot of them is twofold. First of all, we don't know what the real one will be yet, but I'll get to that. And second of all, it's interesting to see how things like this affect the system, because physically, a lot changes with boundary conditions. You can get different densities of states. You can also get zero modes in Neumann conditions, etc. So we take this in the volume with the boundary conditions. I'm going to consider some sort of a decomposition. So I'm going to have a possible zero mode, and then I'm going to have a mode sum solutions over global modes. So those modes are gm of x. Here is an example. In a cylinder, you're going to get Bessel functions. So these are going to be the g's. There's some sort of global functions on your entire volume. You use that decomposition in the Hamiltonian, and you find the quantum harmonic oscillator that tells you how the modes themselves will evolve. You put them into a two-point function, and you get these sort of nasty equations. So I've made them easy by just saying, labeling things by f, where f are some functions that we find and report on. They depend on the geometry and other things, but you can find them. And you find that whatever you can measure, the field or the conjugate momentum, if you can make the two-point function with space resolution and over time, you can invert this relation to find Q, R, and P at t equals 0. You can also process this over time, which is done in this recent papers, and see the evolution over time of this. So in principle, if you have one quadrature of spatial resolution and over time, you in some volume with some boundary condition, you should be able to do something like this. So I wanted to give you just a little theoretical example for now. I'm going to take a field in a square geometry at 300 millikelvin, so pretty high temperature for fields. It's going to be pretty classical. And I'm going to divide the system into A, blue, and B, white, and look at mutual information between them. And you see that as the volume varies where the boundary doesn't, it just kind of moves, but the size is the same. Mutual information basically doesn't vary. There is small variation, but they're explainable by this fit, the black line, which accounts for finite size variations. You can also have a little play with different shapes of regions. So this is one example. You can split it in half in terms of volume and then just undulate the boundary. That increases the area. So you can actually track the mutual information changes with area. And you see linear or sublinear growth. So you're evidencing sort of aerial or like behavior. But I'm still showing you theoretical fun predictions out of easy things. Why am I not showing you data, even though we're collecting it already? There's some issues. So first of all, we need to know what the boundaries are, which in helium, as I said, is rather difficult. They're controllable in some way. You can engineer setups with a different angle at the edge to control the reflection, etc. But it's not known exactly what it is. Also, we need to check how good that linearized model does. Obviously, it's not going to be good for all time. There'll be some nonlinear effects, but we want to see how long they take. So we're still working through that before we report on these things. But also, we already have ideas of what to do next, right? So first of all, we want to be able to control the state a little bit. So we're implementing, putting electromagnetic fields into that cell to control the superfluid helium state, possibly even quench it. We also want to go down in temperature because so far, even if we measured something like this, it's going to be way in the classical regime. Still kind of interesting, but we obviously want to go down in temperature and get better detection methods and try to get it in the quantum regime. So this is kind of the pathway. I'll just talk you quickly through the summary. So I've showed you the thin film simulator that's being developed. I've told you about how you can access information in it, and somewhat more generally, so if you have a system that kind of resembles something like this, then we should do it as well. I've kind of argued that helium is an interesting one to look at, and even though it's maybe an ambitious experiment, versions of it will be complete within a decent time frame. And the quantum regime, I think, if you buy yourself a guinea pig and treat it well, that guinea pig will be able to see it within a lifetime, even if you maybe can't explain it to a guinea pig. So yeah, thank you, and I'll just leave you with a slide of all of us in the gravity group. Thank you.
It's really, it's really, the digital fridge. So and
Sorry, can you speak louder?
it's going to be built next
Mm-hmm. Yep.
year.
Yeah. So in the current fridge that we have, the frequencies are anywhere between 100 hertz and 2000 hertz. In a dilution refrigerator, those will change quite substantially because the gravitational force of the surface will be different from the van der Waals interaction. I think they'll be slightly higher than that, but don't know the numbers off the top of my head for that one. Thank you.
Burning water 10 minutes. And hold up with that.
Thank
What is your name?
you. Good Pahu.
Gupal?
Good Pahu.
Singh. I know I have a burning policy. Coming out with reference to relating from.
Thank you for the introduction, and thanks for having me give the talk at RQI. Thanks to the organizers. Yes, so this is a collaboration with Barbara, who's here. Rick, we all know, he's around. And PA, who's also a collaborator. He was a PSI student with me, PSI master students at Perimeter. Okay, so let's start. Trajectory predicted quantum computing. Sounds fancy. Let's see what it talks about. If I can get this to work. Yes. Right. So the outline is just motivation. Then we'll talk about the literature reviews. This is slightly which just goes through what is the phenomenon of acceleration-induced transparency. Then, yeah, how do we use that to prevent decoherence in qubits, and then building quantum gates while protecting them, and then finally the summary. So let's start. We have two contradictory goals. Goal one. So we have a bunch of qubits, which we see on the right. Then we have environment at the same time, which are lasers acting on the qubits or just stray fields in a cavity, for example. We need to isolate our qubits to protect them from them, right? For them to maintain long coherence times. And then at the same time, we also want some of this environment, like the lasers, to act on the qubits for the computational gates, for the gate operations, right? The question is how to get these two contradictory requirements to work together. So let's build the setup. So we have qubits, which are just undergate detectors, two-level systems with energy gap omega. Then there's an environment, which is a scalar field, phi for simplicity. Then we have the interaction Hamiltonian, which we've all seen till now, I think. It's lambda, which is the coupling constant, mu, which is the monopole operator for the undergate detectors, sigma plus, sigma minus are the raising and lowering operators for the undergate detector. Then phi, the field, evaluated at the trajectory of the undergate detector, which is very important. And we have the ladder operators, AK and AK dagger, in the field, right? Now, note that when you multiply these two terms, you get two rotating terms and two counter-rotating terms, sorry. And then the rotating terms, as we know, they are just resonance transitions. So you shine light on the ground state and it transitions to the excited state, right? And the other one as well. So we have stimulated absorption, spontaneous emission, and this is the primary channel for decoherence because it's higher in magnitude. The other terms are counter-rotating terms. which are like I shine light on the excited state of the atom and it comes down. So it's non-energy conserving transitions, stimulated unruh, spontaneous unruh, and as I said, that they are orders. These terms are orders of magnitude lower than the other terms. Okay, so how are we dealing with decoherence? So imagine you have a state psi f, which is a field state after it has been decohered. So the transition amplitude is just this with the interaction Hamiltonian. The term I plus and I minus are given by these all the exponential terms that you saw in the previous slide. Just take them out and put them in this expression of I plus and I minus. You see the blue terms, these are the rotating terms, the red terms are the counter-rotating ones. The I plus and I minus terms are parametrized by the trajectory x mu. So we have the control over how the qubit moves. Now, the probability amplitude, the transition that your state will actually be a decoherent is a state which has decohered, is given by this expression, the pi to f state. And in that, you see that we have I plus I minus in front of the coefficient of stimulation by the field A dagger A, and I plus sitting there. So what's the goal? The goal is, well, I minus is, as I said, bigger than I plus, so we want that to be 0. And I plus is already small, so we just work with that. The question becomes, is there a trajectory such that at a particular k and omega, k which is the mode of the field, omega is the gap of the detector, is there such a trajectory which gives I minus to be 0, right? So we want the blue term to be 0. That's the takeaway from this. Turns out that there is one. Barbara found that in 2022, that there is a trajectory given by something which is inertial, then accelerates, and then becomes inertial again, the one on the left. On the right, the curves we have shown of I plus and I minus, plotted against the gap of the detector. As you can see that there are two peaks, there are two delta functions corresponding to the two inertial parts of the trajectory. So when it's at rest, you shine light, there's a infinite probability of it transitioning, right? And then there is another one on the right side. But then there is a sharp dip which comes from the accelerated part. And so this is the acceleration-induced transparency. Important part, I plus is not 0 when I minus is 0. So we work with I plus from here on, right? A problem about this trajectory is that it is not compact in space and time. As you see, the integral is minus infinity to infinity. Our quantum computers, well, it's nice if we have them to be finite sized and if we do computations finite time. So what are the requirements? We talk about the contradictory goals again, but this time with the knowledge that we have. We want underdrive detectors as qubits in a cavity which has a single mode. So we work with single mode approximation. And then we want it to be compact and periodic, 1. We want transparent, that it's transparent to the mode I minus, 2. And third, that that the Hamiltonian is periodic, right? So we want periodicity in time. It's nice if we also have a periodic Hamiltonian. Why? Because then if we have, say, we have this cycle 1 and cycle 2 and cycle 3, they are all the same. Like there are no phases at the end of each cycle. There are no phases left. So you apply the unitary, and it's the same evolution here and same evolution here. So the I minus is 0 after each cycle, but I plus doubles here, triples here, and so on. So it's very simple. There is no complications, no phases at the end of each cycle. So that's nice. These are the 3 conditions we want for the first goal. For the second goal, well, remember that we put I minus to 0 in this expression, but we still have I plus on these sides. So, and which is not 0. It's small, but it's not 0. So we use that I plus to do our gates, right? So we do that to do our single qubit and 2 qubit gate, which is the stimulation. You can say, oh well, I plus is very small. How do you work with it? Well, we actually stimulated with this term, right, which is the number of photons in the field. For example, for a Fock state, this is just simply that, and you can put more photons in your field so that this term pumps up, for example. And yes, if we can do single qubit and 2 qubit entangling gate, it's a universal gate set. It was proved by this group in it was 2003. I think that's a type. Anyway. Promising candidates for the trajectory. So now we are designing trajectories. So we have the zigzag one, which is similar to a circular acceleration, as you see, which is nice because then you can just control it with a magnetic field because the qubit just goes around and around, right? Yes, so we took a long time to search in the parameter space of trajectories. to find which one satisfies both transparency and periodicity, the two conditions that we want to satisfy. And the one which does it looks something like this. I know it's not very impressive. Well, if you it's kind of like a vampire like lying down with like two unequal teeth. If you don't see it, that's there. And we have yes, transparency. So how do we see this? We have plotted the real part of I minus and the imaginary part of I minus. It's a complex term, and wherever they are, wherever the intersection of the zeros of real part and imaginary part intersect, that's our actual zero of I minus. VC and TA are just like two parameters out of, I don't know, 16 parameters that we were playing with here. So, but at least we have some intersection. So that means for those parameters, P1 and P2, at those values, we have exact transparency. We have I minus equal to 0. So that's first condition satisfied, and also periodicity. So first condition satisfied, great. Goal 1 achieved. Goal 2, let's do the gate operations, right? Now we have a qubit, we have shining light, we are shining light on it. We just do perturbation theory. So we have the unitary with the interaction Hamiltonian. Then we have this qubit light density matrix, where F is the field simulation. And then for single qubits, you just use one density matrix of qubit A. For two qubits, you use the tensor product of A and B. And very simply, what you do is just, okay, you apply this unitary U on the qubit, you trace out the field, and you do perturbation. You do perturbation on the unitary. So that's easy. That's very conventional. Great. So what do we get? For the single qubit, our field is coherent state. So we are in a cavity. We have this qubit going on in this weird trajectory. And now at each end of the cycle, a gate is performed. A rotation of the qubit is performed. How much? The angle is given by delta, which is some function of alpha and I plus, right? And yeah, so the state of the qubit is just some rotation by delta along some axis n. So great, we have a single qubit gate. You shine coherent laser, do it in these cycles, and you get rotation of your qubits. As you see on the block sphere, it gets rotated. It's just a pictorial representation. This actually was already found by in a paper. Eduardo and Akim had a paper on this. We got some second order correction terms here to their expression. Great. Let's go to the final gate, the two qubit gate. So we have again the same field interacting with the qubit. Do second order perturbation, get this density matrix. There are some rotation terms, noise terms. The important one is the M, the curly M that you see in the red. That's the entanglement part. It has two parts. It has the vacuum and the stimulation. Vacuum contribution just it's just there, and the stimulation is through the field that you apply. Calculate negativity. If you see the expression, we have a positive part minus a negative, another positive part here. So it's a G dagger G, which is a positive operator, and its expectation value is positive. And so that the minus sign there is a problem. This one. The problem is that if you increase stimulation in the field, this term is always going to go up, the G dagger G term, and it's in the minus. So the total entanglement is always going to go down if you stimulate the field. So what's the conclusion? Acceleration-induced transparency is so strong that it prevents you from decoherence, but it also does not let you entangle. There's some tug of war going on. Like you want to protect your qubit from the noise, but you also protect them so much that they can't entangle with the other qubit as well. So there's a nice theorem about this in Easton Hill theorem. We can talk about this later, or you can ask Barbara. So what do? We have, so first we use coherent state. With the coherent state, the G dagger G expectation value is 0. That means you only get vacuum contribution. This is a known result, another from Eduardo's paper. A coherent state can never entangle qubits. The only contribution comes from the vacuum. Great. Then we use squeeze state. Well, the squeeze state expression looks like that. The big theta is just some function of the squeezing angle, the distance between the detectors, blah, blah. Anyway, the important part is the graph. You see negativity, it goes down for most of the parameters, but for one specific angle, theta equals to pi, it actually saturates at a value. It goes up and saturates. So it's good and bad news. For most values it comes, so you need to tune your parameters such that it goes up. it's at the same order of magnitude as the vacuum entanglement. As you see, there is like no orders of magnitude increase, which is not a good news as well. So goal 2 achieved, you see, but well, we're not very happy about it. It could be better. Great. So the summary. So we used the acceleration-reduced transparency for protecting the qubits from noise in the cavity. We found a trajectory which respects transparency and periodicity, which is good. Then we implemented 1 and 2 qubit gates with the counter-rotating terms, the I plus terms, which are small. Turns out that we protect them so much that they don't entangle very well. So that was the whole, we got goals achieved, but the entanglement part, again, could have been better. So that's it. Thank you. Mhm. No, like we are not doing it, and I'm sure there are people who do move qubits in a cavity, but like
So I want to where is the
yes. So what you can do, in principle, what I can think of is that you have some electric field which switches sign from side to side, and so the qubit is moving, like it just gets moved here, then moves here, then moves here. It's switching signs from side to side, or you have a magnetic field which makes the qubit go round and round. That's another way of moving the qubit. But yeah, well, there are always caveats with all these. If you use a time dependent field which does this, there would be extra photons going in the field, which you don't want. You actually want to protect your qubit from the photons. But when there is a charged particle and then you move it in or you accelerate it, there is some radiation going on. So there are some challenges to this approach, but let's see how this goes. Yeah.
Steve? Start is the registration data.
Thank you. Buongiorno. Molte grazie to the organizers. I'm Cisco Gooding. I'm going to be talking about quantum back action and analog spacetimes. And this is based on work done in collaboration with Nottingham and Vancouver and Vienna. One second. All right, so the focus of this talk is going to be on disturbances caused by observing systems and how those disturbances feed back into the observations made on those systems. So I'm going to start off with 2+1 relativistic field plus detector analogy, and discuss how to describe perturbative back action with superfluid helium in this analogy. Then I'm going to move on to non-perturbative back action in a laser-coupled BEC system. And finally, I'll conclude with a discussion of how balancing back action and shot noise is crucial to getting an optimum measurement of BEC signal in this system, and how exploiting correlations between back action and shot noise can take you beyond that standard quantum limit defined by the optimum noise. So just as a quick in passing, there's a bit of a precedent for classical back action. We did an experiment in the Black Hole Lab in Nottingham in 2021, and it describes kind of an adiabatic dynamical analogy that you can get in a black hole analog system. But jumping right into it, the main first topic will be a relativistic analogy in a superfluid thin film system. So if we think of a thin film filling up the XY plane, and it's got some small height h naught, about which there are some quantum fluctuations. Classically, they're called eta, but they will be eta hat when we quantize it. And long wavelength fluctuations in the system correspond to a field that behaves like a Klein-Gordon field, with the speed of sound or the speed of wave propagation replacing the speed of light. And when we interact this 2+1 effective field with a laser that's coming up from above and intersecting at a point, traversing a path, capital X of t. And it obeys this interaction Hamiltonian, where E is the square of the electric field and eta is the effective 2+1 field that corresponds to fluctuations about that surface. Now this laser is going to be described by an electric field like so, where E naught is the coherent amplitude of that laser, and there are some fluctuations about that coherent amplitude that have the same statistics as vacuum fluctuations. And so they behave like this. These little delta A hat of news are the vacuum fluctuations in the system. And the nice thing about this system is that if we think about the interaction term, which is quadratic in the electric field, the linear part has a structure that if you neglect rapidly oscillating terms, it behaves like something that has a built-in switching function, this A naught, that corresponds to the coherent amplitude of the field, and this continuum of vacuum fluctuations. Now, rewriting just that linear part of the interaction, it looks very much like an under DeWitt detector effective Hamiltonian, with lambda being this collection of constants in the system, and this mu of t, the monopole moment, being expressible in terms of this continuum of energy gaps for under DeWitt detectors. So we have this, this collection of under DeWitt detectors interacting with this effective 2+1 field, and that's the analogy at the term at the level of action. Now the nice part, once you do a little bit of perturbation theory in the interaction picture, which Leo graciously provided us with, you find that you can express correlations of these quantum fluctuations in the field arising from back action from the laser. In terms of this nice decomposition of a piece that comes from the classical fluctuations, from the coherent amplitude of the laser, and a piece that comes from the quantum fluctuations. The nice thing about this structure is that the correlations in that quantum field coming from back action are expressible just like an under DeWitt detector would back react onto a quantum field through its interaction. But if you have an integral over a whole bunch of different energy gaps. under DeWitt detectors. So this is the nice analogy that holds at the back action level also, not just at the kinematic field level. And if you do a little bit of rescaling, you can make this switching function look more like the usual one. It goes between 0 and 1, and there's an extra constant that you can absorb related to the power of the laser. And if you want to compare whether we could observe these quantum fluctuations arising from back action, you can take a look at what the square of the classical fluctuations on that field coming from back action are, and what the variance of the quantum fluctuations coming from back action are. You can just look and see from general scaling considerations that at high laser powers, the classical back action dominates the system. So we want to think about like what happens at lower laser powers. If you go to a kind of unrealistically low laser power, you see that, which is 10 hertz, so 10 photons a second, it's kind of below what you would reasonably want to do in the lab. But just for the sake of looking at the behavior, you find that close to the black, or close to the interaction point, there is still dominance of the classical field. But after a certain point, you can see that this green line, which represents the quantum correlations from back action, starts to grow a little bit above the classical part. So there may be some hope of separating the two and observing these through some sort of surface reconstruction methods like they do in the helium experiment with the vortex. And Adam was nice enough to do a whole bunch of numerics for this. He generates these really fun spiral patterns that represent back action coming up and spiraling out from a point of interaction. More of these will come once we finalize the paper, and it should be out later this year. But we'll contrast this perturbative back action with what structure that we have in the UNR proposal that Jorma mentioned a little bit earlier in the conference. Basically, we have a pancake BEC and we intersect it with a laser. And in the UNR proposal, we deflect that laser interaction point along a circle and try and extract some information about the so-called circular UNR effect. But we don't actually have to make it a circle. We could put that trajectory any way we want, and we could still do the same analysis and try and pull out a signal of the BEC interacting with the laser to see what we would get. The field in this particular analogy is representative of density fluctuations in the BEC in this pancake. And along this similar trajectory, x of t, which at this point is arbitrary, we find that we can build the same kind of things that we like to think about in RQI scenarios, like the response function of a detector, in accelerated motion and things like this. And we can build them out of this effective phi field that's behaving as a relativistic scalar field. And now the question is, how do we pull that response function out of the laser as it comes out of the BEC after it's interacted? And so the rest of the talk, I'll talk about that signal and what the role of back action is in trying to pull that signal out in the optimal way. I won't go into the details of the experimental proposal, but this is just an optical circuit diagram of things that you have to do, modulating and splitting up various things to protect the BEC from disturbances, and split parts of the output signal so that you can extract them with a heterodyne scheme. Ultimately, the details of that part aren't crucial. What matters is that the laser fluctuations, this delta A plus or minus tilde, plus or minus correspond to 2 modulation peaks. They have a particular structure where the output laser, yes. The output fluctuations in these around these two modulation bands are given by the input and then some signal from the BEC. These D operators are just the creation and annihilation operators for that effective scalar field. And then you get some extra terms that are quadratic in the effective coupling, and they represent the back action in the system. Bill, in this paper in 2022, published this Bogolubov method that he used to express the interaction non-perturbatively. And so this is basically, you can think of an expansion in this mu parameter, except it truncates exactly at second order. And the nice thing about that is that you can express that complete interaction in just those terms without worrying about missing any of the higher order pieces, because there are none. Just quickly in passing, we use a heterodyne scheme to pull out the signal out of each of these two modulation bands after splitting them apart. And the result that you get from that, skipping the details of the heterodyne detection, is that in the photocurrent power spectral density, we have a shot noise contribution, response function exactly of the form from accelerated detectors in 2+1 relativistic fields, and then back action correlations, and an interesting shot noise back action correlation term that appears at the exact same order as the signal. So a lot of the times we think of back action as this like smaller, higher order effect, but in this situation, it appears at exactly the same order as the signal we're trying to extract. So it should be much more observable than a lot of back acting systems. The standard quantum limit then, just as the last topic I'll bring up, it corresponds to a balance between the two contributions coming from shot noise and back action. At low laser powers, the shot noise is the dominant term, and then you increase the power to try and reduce the relative shot noise. And when you do that, back action starts to dominate. And then in the middle, there's a minimal noise part, and that corresponds to the standard quantum limit. If we squeeze the incident beam, we can go below that limit. And ultimately what that's doing is it's incorporating correlations between the back action and the shot noise in the system and exploiting those correlations to dip that minimum below the standard quantum limit. And this is just a picture that Cameron generated of exactly how far below that standard quantum limit that you can go with squeezing. And here lambda is the squeezing parameter. And it takes not a whole lot of squeezing to dip below, and unity in both the plus nu and minus nu sides of this response function represent, compared to 1, how far down you can dip below that standard quantum limit level. And so just as the last thing I want to say, there's a question about whether or not we were going to cook this pancake. We need a certain power to reach the standard quantum limit, and we didn't know for a long time exactly whether we could reach that limit without cooking or destroying the BEC. We ran some numbers, and it turns out that it doesn't disturb the BEC at all, or very much at all. So the scattering rate of knocking atoms out of the BEC per second is well below a hertz, which is usually the limit for non-destructive measurements. And the same thing happens with the squeezed case. It gets a little bit higher, you scatter a bit more atoms out, but it's still well below the threshold for a non-destructive measurement. So just wrapping that up, the conclusion is that we can reach and beat this standard quantum limit to optimally pull out a signature of the Unner effect, or just general response function effects for arbitrary stationary trajectories. And ultimately, we can cook the steak without cooking the pancake. So with that, I would just like to say thanks for your attention, and here are some ringraziamenti for the rest of my collaborators. Thank you.
Great. Thank you.
Yes, yes. Thanks for the question. So in both the scenarios, the superfluid helium thin films and the BEC, the levels are really just shifts of the photon in frequency. That's why you have a continuum of them, because there isn't a two-level detector in there. In the first situation, you get a continuum of detectors of different gaps. In the second situation, you don't have that at all, really. All you have is a response function signal coming out of the laser. So it's a signature that corresponds to what two-level detectors would do, but it's not. There are no two-level detectors. Yes, 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 absolutely.
You can here.
Or what do you have?
HDMI.
Oh, it's
Yeah. USB. But either USB. Okay. Okay. Thank you. Thank you. Hello, everyone. So as I was saying, I will talk about in a similar spirit to the previous talk of Cisco, I will talk about an experimental system, but in this case, it will be superconducting circuits. And I'll talk about how to relate it to a particle detector model, and then what are the consequences of this model for entanglement harvesting when we try to do an implementation. And also, I'm not the Adam that Cisco was mentioning in the previous talk, which he helped. I am not. And yeah, I will give again the reference at the end for the work on the archive. So to start with, one of the protagonists that we need to talk about entanglement harvesting is the Unruly detector model or particle detector models in general. These have appeared in the conference several times, like for instance in this morning with Rob Mann, and also Mateus also talked about them. And I will briefly mention an example of it. So here we have the interaction Hamiltonian for the Unruly detector model. One of the first elements is we have, for instance, a coupling strength that multiplies everything, have a switching function that localizes the interaction in time, and we have a smithing function that localizes it in space. And then we have the field, which appears to the right, and it's expanded in plane waves, a scalar field, for instance. And the monopole moment, which is an operator of the detector, which, for simplicity, we are considering a qubit, and it has a certain energy gap, qubit gap, that will appear again later in the talk too. So this is a very idealized model. It works well to do theory. And one of its predictions is that it allows us to do entanglement harvesting, which basically is this prediction that we have two detectors, A and B, here in this diagram represented by the gray areas. So we have a gray area A on the left and a gray area B on the right. They are spatially separated. The light cones do not touch the interaction region. And even though they cannot communicate because they are spatially separated, they can get entangled. So this is entanglement harvesting. And currently this is a prediction, but there are several experimental proposals for it. One of them that I'll be talking about is superconducting circuits. There is also proposals in graphene, also in Bose-Einstein condensates using the system that Cisco was talking about before, and nonlinear crystals. So why would we prefer to use superconducting systems, for instance? Well, because they have this very useful ability to create artificial atoms, so like a quantum system that can couple to the electromagnetic field, and we have very high control over this coupling. It can be coupled very strongly, and the coupling can be turned on and off with very fast. I see now that it's slightly cut, but it seems it works more or less the slides. So now, how do we actually, in detail, bring these detectors into the lab using superconducting circuits? So an overview of it, if we want to like match each part of the Unruly detector to each part of the implementation, we could start with the detector on the theory model side, and we'll consider a qubit with a certain energy gap again. So this is the separation between the energy levels. And simply for the implementation side, we'll use a superconducting qubit. Then the quantum field part becomes a bit more tricky. What is easy to implement on superconducting qubits, or superconducting circuits, sorry, is a one-dimensional quantum field. The way to do it is to basically have a very long superconducting cable. And that is also called a superconducting transmission line. and it behaves as a one-dimensional quantum field. And then finally, we need the switching function, the turning on and off of the interaction between the detector and the transmission line. So about a little bit more detail about this transmission line, and it's a long superconducting cable. The way that it's usually, this might be a little bit intimidating at the start. It's the way that it's usually modeled in superconducting circuits, and it's a discretization of it is several chunks, delta x, and a certain density of inductance and a density of capacitance. And then there is the phi on top, that is the integral of the voltage over time, and that is what it will be our field. So a way to see that this is a quantum field is that you can take the delta x going to 0, so removing the discretization, going to the continuum limit, and then you get that the Hamiltonian of this system is this one here, which you might recognize as the one of a one-dimensional massless scalar quantum field. And again, one thing that is a bit different is that now we have these constants, the density of inductance and capacitance, which will combine to get a different velocity, which is not the speed of light, but can be lower than the speed of light. So waves propagate slower in these transmission lines. Next, we need to the part of the device, which is the flux qubit, or the superconducting qubit, and the coupler. So these two loops are made of a cable, superconducting cable, but with some interruptions. These crosses here, they are also called Josephson junctions, and they do the magic of creating a qubit and a coupler. And then we need to couple it to the transmission line. To do this, we place it in the transmission line. So you can see there at top, there is an A and a B here. They are placed here in the transmission line, like connected, the cables touching each other. And the way to tune the coupling in this device is by changing this magnetic field here. This is a magnetic field that threads the loop, and by tuning it, you can tune the coupling between this qubit at the bottom and the transmission line. So this is the actual thing in the lab. There's an electron microscope image of it, and you can see the transmission line. It's one of these cables in top of the circuit. This is made the same way that silicon chips would be done. And then on the left, you can see the two loops. One is the qubit loop and the other the coupling loop, and they are attached to the transmission line. And then the bias lines control the external magnetic field, so they control the coupling. Okay, so now that we have the experimental model of the implementation, that was not an unruly wave detector. How do we, or it did not seem to be an unruly wave detector. How do we make it look like? How do we bridge the two models? So the one that I will start on the left is the circuit model that I presented before. This is a good representation of the experiment that is usually used by experimentalists to model it. Then we need to connect it via some bridge. This is a bridge that is close to where I'm from. I was built by the Romans, but now only the arch is Roman anymore. The rest is revealed later. And then we need to bridge it to a model that resembles an unruly wave detector. So what is this bridge? This bridge would be first taking the continuum limit, as I mentioned before, but also there are more tricky parts to it. These more tricky parts are doing some approximations to simplify the model. So, for instance, I mentioned that it was a superconducting qubit, but actually this system here, if you take the Hamiltonian and you look at it, you will see that it has infinite energy levels. You need to make an approximation that only the two lowest energy levels matter. And it's a very common approximation to build superconducting qubits on the lab. Then also the free detector should not, the free detector dynamics should not cause excitations of the detector. This might happen because we are changing magnetic fields that can induce transitions. We don't want that. We only want the transitions happening because of coupling to the quantum field. And to avoid this, we can do an adiabatic approximation on the free dynamics of the detector. And then to simplify the coupling so that it's a simpler model, we remove some parts of it and only keep the transversal one, which is the common one in unruly wave detectors. So we remove, for instance, if in terms of polymetrices, we remove the sigma z. It's small usually. And then we get a detector model, which resembles an Rudewitt model. And I will give now the exact expressions. Okay, thank you. So this is I will go slowly through this, just pointing out the differences. We don't need to go, we don't need to understand it deeply. Just I'll compare it with standard and Rudewitt model. So this is what results after doing the approximations that I mentioned before. It needs some calculation. It's not immediate. But the first thing I would like to point out is that the interaction Hamiltonian between the detector and the field couples to the field derivative. Here, the partial x. The next thing is that the coupling, instead of coupling to the field, we consider the detector couples to the cutoff, a field with a cutoff. This is to match better the experimental implementations. They are usually talked about them as having cutoffs because some very high frequencies escape the transmission line. But this can also be thought of as the detector having a limited spatial resolution of the field, like a smearing. It can be related to that. And finally, another feature of them is that now the energy gap of this qubit, it is not constant, which would be a simple assumption that we would do to make the calculations easy. Instead, this energy gap depends on the coupling strength or on the switching function. So here we have a constant term plus a linear part on the switching function. So when we turn it on and off, the energy gap changes over time. So now we have this model, and we would like to know what are the consequences of using this theoretical model that is closer to the implementation. It's not a fully accurate model of the implementation, but it's closer. So what effects would it have on the entanglement harvesting experiment that could be done in the future? First, to be able to explore this, the model that I talked about had several parameters that we need to fix, to choose. There are some that are forced by how we implement the device. Once you build the device, they are fixed, and we chose them to match the implementation. And then there are some other parameters which are more that we can explore, that we can tune on the fly as when the system is already built. And these there are choices that this can be, for instance, the initial state of the detectors, the coupling strength, and the switching functions. And for simplicity, for what I will talk about next in the next slides, I'll choose like the detectors to start in the ground state, the couplings to be equal, and the switching functions to have the same shape and be displaced one with respect to another. The shape is something like this for the next slide. Like it goes up as a sinusoidal ramp, then it's flat for a certain portion of time SF, and then it goes down. And it's compact, so that we can talk easily about spatial separation. And then as a diagram, this would be again having the gray area of interaction, time that it takes to propagate signals from one detector to another TD, and one detector happening switching on after the other with a time difference T delta. And these are the plots of the entanglement that the detectors can get when they are in spatial separation. So spatially separated detectors, this is the exact choice. We put them at 1 nanosecond of distance and turn on and off the interaction faster than 1 nanosecond here at the bottom axis. And the vertical axis indicates the shape of the switching. Then here we are plotting the negativity as a measure of entanglement. It works well for mixed states, that this is what we get after this. And we can see on the left what we would get if there was no gap variation. For instance, this is exploring what happens because of the gap variation. There is certain places where we can harvest entanglement. If we turn on the gap variation, and by using a larger coupling strength, which induces more gap variation, then many of the parameters for which we had space-wise harvesting don't have it anymore. But there is still some, as long as we don't get gap variation that is too large. Now, another thing that is interesting to look at is what happens if, instead of looking at space-like separation, we look at detectors that are in causal communication, that can send signals to one another. Again, now I'm considering a setup with gap variation. And this diagram here, it doesn't appear on the left, but the horizontal is the distance between detectors. The vertical is the time delay. And we can see that, is it time? Ah, okay. I see. Okay, yeah, then, yeah, just that there is an estimator to look at whether entanglement is harvested or not. And we can see that there is some ways to get entanglement harvesting. And just to conclude, superconducting circuits can be carried to the lab. We upgraded the Android detector to get implementation features, and in the future we'd like to get a more accurate model and experimentally verify entanglement harvesting. And this, for more details and more plots, you can add this reference.
What if the switching function depends in the gap so that you like parametric resonance to mass still instead of suppressing?
There might be. We like definitely there is like exploring all the possible shapes of the switching function is not something that we have done yet. So there might be ways to use that. Also, the switching function can become negative in this setup, and that might also enhance entanglement by using some resonance with that. So that is a good question.
Yeah, thanks. Can you hear me? Good. Okay, so this is going to be a very different talk from the previous previous ones in the session, because it's going to be entirely theoretical. But the hope is that it will contain a suggestion for how to move on the experimental side concerning gravitational dynamics in analog systems. That's the topic. So I don't have to convince the audience that analog gravity is great, but so we know we can reproduce a quantum field theory dynamics on a curved background with some generality in condensed matter systems, because we know that the excitations over ground state coupled to an emergent geometry, an emergent metric, not the laboratory one. And this is great also because the type or the class of emergent geometries we can reproduce in this way is quite broad. It contains, it includes a number of spacetimes of interest for cosmology, for black hole physics, and so on. So all this is the stuff you know. And from the quantum gravity perspective, which is where I come from, analog gravity systems are also intriguing because they seem to be at least partially a concrete example of the idea of gravity being an emergent phenomenon and space-time geometry and fields, in fact, being collective entities from something else, which is in resonance, at least, with a number of ideas put forward in a quantum gravity camp. The big open issue is that the consensus is that you cannot reproduce gravitational dynamics in the same systems, because the main point being that the emergent curved geometry is a function of the hydrodynamic variables. The hydrodynamic variables for your fluid satisfy the hydrodynamic equations, and hydrodynamics is background dependent. It depends on the metric of the lab. it has a special set of symmetries which have nothing to do really with the diffeomorphism invariance, the gauge symmetry of general relativity. And this brings a number of strong constraints on what you can do, strong limitations. From the gravitational, maybe even quantum gravity perspective, there are a bunch of other suspicious aspects about the analog gravity context. One being that localization in space-time is defined in terms of manifold points, coordinates, all the things that from classical and quantum general relativity we are suspicious about. We know they are, gauge artifacts, they are redundancies. Now, the main point, again, is that hydrodynamics is different from general relativistic dynamics. You cannot reproduce general relativistic dynamics for the curved metric starting from hydrodynamics. That's the main point. That's the consensus. In fact, you can. The starting point of the proposal is that, in fact, at least at the mathematical level, you can reproduce, for example, cosmological dynamics from hydrodynamics. And I'll show you one example. I mean, there are a number of examples that are known. One is quite old, more than 20 years. You can take the Grosspit-Hesky equation for an interacting BEC in a special case in 2D with a certain parabolic trappic potential. You can encode the dynamics of the system in a bunch of integral moments, which are basically hydrodynamic averages, average quantities using your condensate wave function. And these are written here. They satisfy a bunch of equations. You can do a bit of mathematical cosmetics, and you turn the equation satisfied by the moments into the Ermakov-Pinning equation. So far, so good. Cosmetics with hydrodynamics, a game in mathematical physics. Intriguing, if you take the Friedman dynamics, the Friedman equations for the scale factor in the isotropic homogeneous context, so gravitational dynamics in a very simple context, with a scalar field with arbitrary potential, you can do a different type of mathematical cosmetics, and you recast the dynamics for both the geometry and the matter field in the same mathematical form. They do satisfy the same equations, the geometry and matter in cosmology and BEC hydrodynamics. And looking at this transformation, you can see, well, I could have obtained it if I didn't know about the earlier results by a specific map between the moments computed within hydrodynamics of the BEC and a specific set of observables, quantities in the cosmological system. And the map is here. The other objection against reproducing gravitational dynamics in BEC, in analogous system, had to do with the symmetry. But if the dynamics is the same, at least in this case, you should expect the symmetries to be the same. How can that be? Well, first of all, before moving there, intermediate step, you could see the map between integral moments in hydrodynamics and cosmological quantities as extremely natural if you look at the same hydrodynamic system and you just translate it. You just change the name of the variables. You don't have to do anything. You just change the name. You say, well, suppose that this system, instead of being defined on space-time, meaning the space-time manifold, the redundancy of GR, in fact, R and T, I define it on the space of geometries and fields, on the space of values for the scale factor, the scalar field, and whatever other matter field you have. It's the same dynamics, just you're changing the name of the domain. Then the maps between moments and cosmological quantities I've shown earlier is the standard sort of averages you would do in quantum cosmology, where you have a wave function on mini superspace and you take averages. In that case, it's quantum averages, expectation values, but the same type of quantities, and you reproduce the same map. What about the symmetries? Well, maybe surprisingly, if you look at the cosmological dynamics, it's a mechanical system. you ask if there are symmetries. I mean, one of them is known. Of course, you have reparametrization invariance in the time direction. Time is really like an affine parameter. The time coordinate in GR is really like an affine parameter for the relativistic particle. It plays no physical role. You can ask if there are additional symmetries. And in fact, there are. You can find that there are a set of transformations on the space of values for the fields which leave the system invariant. They are symmetries of the mechanical system. You check what they are. So I'm transforming the values of the scale factor together with the values of the scalar field in a coordinated manner. Okay, and these are the transformations you can find. You check the commutators, and you can show this is the Schrödinger algebra in 2 dimensions, which, by the way, is the same symmetry of the hydrodynamics of the BEC in 2 dimensions that I've shown earlier, which of course, you can derive independently. You take the BEC hydrodynamics, the Gross-Pitaevsky equation, you ask if there are symmetries, it's the Schrödinger algebra, which is basically the non-relativistic version of the conformal group, the conformal algebra. And if you have this such strong symmetry base, then the correspondence between the dynamics is in fact dictated to a large extent by the symmetries, because you can just put in correspondence the cosmological dynamics and the hydrodynamics in terms of, by putting in correspondence the conserved charges or the generators of the symmetry. One side you have specific hydrodynamic averages, which are generators of the Schrödinger algebra. The other side, you have special functions on the configuration space of gravity plus matter, which are generators of the other symmetry algebra I've identified. Okay, so this is an example, but you can show that a similar story applies to a bunch of other systems in cosmology, in gravitational physics. So the suggestion at this level is, okay, maybe I should look at hydrodynamics on superspace, on the space of fields. And then the later suggestion is maybe that's what I have to try to reproduce in the lab with a standard BEC. That is the thing that will give me equations for observables, which corresponds to the gravitational dynamics. So that's the proposal. You take this as a framework, some nonlinear equation for a wave function on the space of geometries on superspace. That's the thing from which you derive cosmology on the one hand, but it's also the type of dynamics you can reproduce in the lab, because it's the sort of equation that you will get from a BEC or any other fluid. So that's the proposal. Once more, I don't have to spell it out again. The fact that there is some background metric is not in the lab and in the hydrodynamics is entirely compatible with the general covariance of GR, because it's the metric in this rewriting on superspace. Generativity comes with a metric on the space of metrics. And that's a background structure in GR, a given topology and so on. It comes with the symmetry of that metric. And that is what matches the symmetry of the hydrodynamic system. Anyway, so there's no contradiction between anything about general covariance in GR and the fact that you have hydrodynamics in a lab with a given metric. You just have to identify the proper system. Okay, the question you may have is that, okay, this is still just mathematics, but even if we stay at the mathematical level, is there a more fundamental support for this? Because I've shown just a map between two systems, but this hydrodynamics on superspace, can it be derived, motivated by some fundamental quantum gravity formalism? Okay, I'll be brief because I have 2 minutes, I think. First of all, this is exactly what you get when you take loop quantum gravity spin-found models. You first, where is it? You first recast them in the language of group field theory, which is an auxiliary field theory for discrete building blocks, and you take a mean field approximation of that. That's exactly the form that the mean field approximation takes. Just like you extract the Gross-Pitaevsky from the atomic microstructure and quantum dynamics. Specifically, you can write down field theories on some domain which is not the space-time manifold, and as it shouldn't be in quantum gravity. you take a mean field coarse-grained approximation, and I don't see, oh yeah, there, and you obtain equations of motion of this general form, exactly a nonlinear extension of quantum cosmology or hydrodynamics on mini superspace, or the form I mentioned earlier. And then from there, you compute appropriate expectation values or averages in this hydrodynamic setting for observables that you can then identify with gravitational quantities like the volume of your universe or the energy momentum of the matter field that you have. Of course, I'm glossing over many details that I guess you imagine, but I'm happy to fill you in on that. And this is something that has been developed independently, of course. People are just trying to extract effective continuum gravitational physics from quantum gravity, and people have been doing the extraction of cosmology in a coarse-grained approximation from these quantum gravity models with a number of results. The point here is that indeed this hydrodynamics on mini superspace can be derived with more or less rigor, more or less amount of details, depending on the quantum gravity framework, from this side of the story. But in fact, it can be motivated and derived also from as an effective way of including inhomogeneities in a standard quantum cosmology setting. This is work by Martin. I don't know if he's around. He was around at least at the coffee break. And it can be seen, I don't know if you know about third quantization or wormhole calculus, how to include topology change in canonical quantum gravity. You can derive this type of effective setting also from that point of view. So that's the proposal again. There's no contradiction between what we know and what we have mathematically in hydrodynamics. And gravitational dynamics, properly understood as taking place on the space of fields rather than on the manifold, which is just a redundancy of the description because of diffeomorphism invariance. And you can try to reproduce gravitational dynamics, possibly also in the lab, switching perspective and trying to identify systems which have the appropriate form of hydrodynamics that we can derive from quantum gravity models, or that we can put in correspondence with cosmological dynamics at a purely classical level. And we started working on this with Toby and a bunch of other people, and hopefully we will continue and deliver. Yep. Thank you.
Today, there is an inverted function.
Let's wondering the cost of living. How does we can see any problems on survivors and what does it mean? It's like regular, I don't know.
Okay. First level of answer is that this is work in progress, because we are trying to exactly show how the cosmological singularity translates in terms of the cosmological quantities mapped then into hydrodynamic quantities, and checking. We want to see how it works. But that's the first step. The other thing we are doing to make sure that we don't talk nonsense, that we want to show that whatever happens in a particular example in terms of mechanism for solving the cosmological singularity, or what goes wrong there, is the same mechanism in other cosmological models. And so it's taking a while. So at the moment, I don't know yet. The other thing I want to say about the cosmological singularity is that all of this map takes place at the mean field level. So what could happen is that you find that the singularity is a breakdown of the mean field approximation. And so you have to go to some more kinetic theory, or if not the full microscopic quantum dynamics. Ero troppo guidato. Strappo.
Okay. Thank you. Okay, thanks everyone. So I'm going to talk about, well, you can see it on the screen. So this is work that I've done with a number of people, and I'm just going to get started. So let's talk about acoustic black holes. So most people in here have heard about these by now. And the idea is that if you have a hydrodynamic system, oops, that's too far. You have a hydrodynamic system, and there's a drain. Then close to that drain, there will be some distance away from the drain. Wow, it is hot. My God. There'll be some distance away from the drain at which the speed of sound is less than the speed of flow of the fluid itself. And there have been some nice experiments done on this. It was proposed by Unruh in the 80s. So here's a black hole, right? This is some Kerr black hole because it's spinning water around a drain. So if that's a black hole, then there should be some relativistic effects. But if I put my watch near it, it doesn't slow down. If I put a ruler next to it, it doesn't length contract. So what's going on? Where is this sonic relativity? Who sees this? What kind of observers would see this sonic relativity? And this is a really important question for a variety of reasons that I usually talk about, but I'll skip in the interest of time. But observers in relativity is a really important thing. Maybe I don't have to convince you of that. So what could be sonic observers? What would be observers that would see this relativity? Well, we know that the problem with this is that the actual laboratory physics is non-relativistic. In fact, yeah, a waterproof watch doesn't slow down in water, so there's no time dilation. The rulers don't shrink in water. There's no length contraction. So the speed of sound is not constant. It is only constant with respect to the medium, the sonic ether. If the medium's moving, then it's not a constant speed. So what can we do? Well, there's a paper that I wrote with a former student of mine, Scott Todd, and there was a follow-up by James Reed and his student, Why Not a Sound Postulate, that addresses this and actually says, yes, you can construct these sonic observers. So here's what sonic observers can do. First of all, they are classical beings. They can count. They can locally discern before, after, and simultaneous. Just locally, though. They can send and receive sound pulses. You can probably see where this is going. Can communicate information and instructions to each other. But importantly, they have no other measurements. They can't sense their own heartbeat. They don't have a sense of the wind in their face. They don't have any ability to make measurements other than by the exchange of sound pulses. Okay, so this is what I use when I teach relativity. So you have these two bats, and they send sonar pulses back and forth. So pulse goes out, the other bat receives it, send a pulse back. First bat receives it and counts the number of pulses that have been received. This is a sound clock. That's a stationary sound clock. When the sound clock is moving, look at what happens. So look at the difference. The difference is that this is the standard light clock analogy just with sound, but it's all Newtonian here. So the sound in the moving clock travels further, but at the same speed. And therefore, according to Newton's laws, no Einstein, Newton's laws, moving sound clocks tick more slowly than stationary ones. Okay. By how much? Well, it turns out it's the sonic gamma factor. Isn't that interesting? I mean, it's not really that surprising because the relativity is baked into the dispersion relation, but there it is. Okay, what about a sound ruler? Well, you have a situation where there's a timing pulse and a spacing pulse, and they need to come back at the same time. So these bats have to arrange themselves such that happens. That is the operational definition of one correct spacing. So what happens when the ruler's moving? So the ruler's coming in. Any guesses as to how they have to organize themselves such that that operational condition is met? Any guesses? They have to be closer together. How much closer together? By the gamma factor. So let's see what happens. So this is what happens from the laboratory frame, the rest frame, the ether frame. But nevertheless, that's what happens. If they come together by an amount given by the gamma factor, then they arrange themselves into what they believe is an appropriately spaced separation. So according to Newton's laws, moving sound rulers are shorter than stationary ones when defined by this operational means. Okay, So, and it's, there it is, standard stuff. So then you can build this up using standard, just like light clocks, build up a reference frame, have a synchronization pulse, all of that stuff. So what you have are these units. A tick is the duration of a single round trip of a sound pulse. In a sound clock, space is the distance traveled by the synchronization pulse during one tick. And the synchronization pulse speed is 1 space per tick in any frame. That's what they measure it to be. Now, of course, we know that it's not the case, but that's what they measure it to be. You get a sonic Lorentz transformation. So in fact, this is reciprocal. So, and this is all from Newton's laws. So what's going on here? How can it possibly be reciprocal? Well, I mean, this is the synchronization. This is what happens when you try to synchronize it in the laboratory frame. And when you try to synchronize it in a moving frame, this is what you get. You get offsets, just like you would in real relativity. And of course, when you move between them, you accelerate, and these frames switch roles. And after the end of the acceleration, you have what was the moving frame is now your own frame, is now synchronized, and the other one is not. And if you compare, look at where the 9 is, just to the right of the 0 on the top. There's a -9 to the right on the bottom, and that's exactly what you'd expect from relativity. Okay, so we can go back and forth. Well, all right, so enter sonic Einstein. So one of these bats is sonic Einstein. It says the laws of physics for sonic observers are the same in any inertial reference frame. And the speed of sound is always measured to be constant using sound-based materials. Okay, so sonic relativity is a dynamical theory. Time dilation is the slowing of moving clocks as measured by stationary ones. This makes perfect sense when you look at it from the laboratory frame. Length contraction is the shortening of moving clocks, moving rulers as measured by stationary ones. And these statements are about the physics of clocks and rulers and the space-time that emerges as merely a bookkeeping device that they come up with that has speed of sound as an invariant speed. And note that the reciprocity of the Lorentz transformation means that while it's not obvious, these do hold in any reference frame. So, all right, so I'm going to skip the summary. What breaks the sonic relativity? Well, a measurement made using anything other than sound. For instance, if the bats could measure their own heartbeat, if they had a meter stick, if they had a ball clock, if they could toss matter back and forth, that would break the sonic Lorentz symmetry that they see. Well, what else breaks it? Well, if you scatter sound from an external particle. An external particle is any particle that doesn't have the right dispersion relation, according to them. So the setup that we have here is we have 2 setups. One, there's some little piece of dust sitting on the medium, and they can scatter sound off of it. But in one scenario, the dust is moving, and so are they. And in the other scenario, the dust is stationary, and so are they. And they can actually see an experimental difference because the dust particle does not obey their sonic Lorentz symmetry. So they should be able to tell that they are living in an ether universe, right? Well, let's see. How would they interpret this? Well, that is one option. They could say phonons travel through an ether. I guess we live in an ether universe. That's weird. Didn't think so, but we do. But there's another option. The external particle travels through an ether. That is, the velocity-dependent effects are relative to the rest frame of the external particle. This preserves the sonic Lorentz symmetry. Now, this may seem absurd, and on the face of it, it is, but I will argue that it's a logical conclusion for them. This is the natural and mathematically rigorous conclusion for the sonic observers. So let's see how this works. By the way, when you stand up, please hold your chair. Yes. Okay. Anyway. Okay, so the external particle, ordinarily relativistic, has this Lagrangian. Okay, and I'm going to use mu and nu to denote the coordinates with the usual speed of light scaling of time. Okay. And you'll notice that I've restored C and H bar here, and that's important because mass m is not the invariant quantity according to a unit analysis. It's actually should have a bar there. It's a reduced Compton weight. It's a Compton wave number that shows up. Anyway, there it is, Compton wave number 2 pi over lambda c. Okay, so the internal particle is one that is sonically relativistic, and that is the equation, that is the Lagrangian for it. And you'll see that it has a different k, but it still has the same form, or similar form. We can define, based on the observers that I just talked about, these observers will have their own AB coordinate system that is sonically Lorentz invariant. So they can use a sonic Lorentz transformation to go between them. There's a regular Lorentz transformation that relates the mu nu coordinates, but they're not the same Lorentz transformation. Okay, so here's the internal sonic particle, here's the external or laboratory particle, and here are the coordinate transformations between them. There's some, they're not lambda, it's not a Lorentz transformation that relates these two frames, it is something else. And also, it is not the transpose that does the inverse. You actually need a different tensor to convert between them. Okay, I can see I'm doing okay, but let me set another timer here, 1 second. Come on. Okay, so we have these relations. The internal sonic metric can be written in either coordinates. So the sonic metric is naturally just one, -1, 1, 1, 1 in the AB coordinates, but it actually transforms when written in the mu-nu coordinates. The external laboratory metric also transforms when written in the sonic coordinates. Both of these are totally valid. Okay, so the external laboratory particle in sonic coordinates does this. That's the usual one, but we want to transform to the other coordinates. So we just do a coordinate transformation on all the tensor indices. And then we have some delta function, Kronecker deltas. They collapse like this. Now it looks like we have a sonic particle, but we don't, because that's the wrong metric for these coordinates. That is the photonically relativistic metric tensor that appears, but it's written in the sonic coordinates. So we got to fix that. All right, how do we fix it? Well, we add and subtract the metric that we want. No problem there. And it becomes this. So what you have is a sonic Lorentz scalar field plus a correction term. It's a sonic Lorentz violating term. It violates the sonic Lorentz symmetry. Okay, fine. So that's what we're starting with. And the same is true when you go in the other direction. So if you look at an internal particle in laboratory coordinates, we're familiar with this. You have sound. It travels in a reference frame. We don't have a problem with that because the reference frame has a medium. The fact that it's anisotropic propagation doesn't bother us. But the other one is strange. So what this looks like, there's some mathematics. The point is that you can rewrite this in terms of a velocity 4 vector of the rest frame of the medium in both cases, in the sonic particle case and in the other particle case. So this is what we get, and it looks like this. So the form is the same. The only difference may be the sign of the prefactor. Okay, so anyway, what does this mean? Well, it means that option 2 is actually the one that they are likely to believe. They're going to say, okay, look, there's some weird particles out there. We're going to have to change what we believe is the maximum speed, but nevertheless, all the symmetries are the same. Okay, and I will just do real fast these because we're familiar with this with drum heads. It's isotropic when you're in the rest frame of the drum head, but it's not if the drum is moving. Okay. And the same is true with what we dub the tachyonic medium. So the internal observers will see a particle that goes too fast, according to them, as living in as being an excitation of a medium that has a rest frame. That is a totally logical conclusion. I showed the mathematics for it. It's all the same. The only thing you have to realize is that now you have a medium that carries excitations that go faster than your Lorentz invariant speed. Okay, so how many people are thinking, what about temporal paradoxes? I hope some people are, at least a few. Good, let's answer that question. So a fully relativistic tachyon can travel at its maximum speed, greater than c. In this case, it's almost infinite, as viewed from all frames. And this can cause causal paradoxes. You send a tachyon away, it gets measured and then reflected back by an observer moving away from you, and it arrives before it was sent. But in this case, let's see. Okay, in this case, we know that temporal paradoxes cannot occur because everything exists in a lab. There are no temporal paradoxes in this room or in any other lab. So how does this resolve for the internal observers? The solution is that the tachyons appear to be confined to a medium, which makes their propagation speed anisotropic. And so it looks like this. They try to do the tachyonic anti-telephone and they fail because the return pulse does not go as fast. It's only in one frame is the sonic tachyon speed isotropic. And this is what it looks like from the other frames. It's not able to go backwards in time. So just real quick, view from the inside, sonic observers can maintain their Lorentz symmetry even in the presence of external tachyonic particles. And the velocity dependence effects are ascribed to the tachyons rather than their own medium. And it's paradox free. Let me just see what I want to leave up there. Yeah, so in reality, the sonic observers are perceiving their own motion with respect to the sonic medium, but they wouldn't believe this. So what I find really surprising is that Lorentz invariant speed in a relativistic model need not be the maximum signal speed. And discovery of medium bound tachyons in our real world, I'm not saying we have them, need not refute Lorentz covariance and need not cause temporal paradoxes. Now, of course, there may be other physics that actually does that, but I will just leave that up for you to read. Thank you.
So, hello. If you want to solve our, would you
General relativity? Yeah. So I'd like to understand that. You would need something like that, and I'd like to see how that occurs. It should be the case, according to Sakharov and Jacobson and all these other emergent gravity scenarios, that some sort of Einstein-Hilbert action should occur when you have a natural fields on some sort of possibly dynamical spacetime. Anyway, so we'll see.
Okay, great. Thanks. Thank you. So we want to quantize relativity. I guess we're basically very interested in that. And what is the problem of doing that? I'll tell you my personal opinion on this. And if you open a textbook of quantum mechanics, you will see that it talks about quantum systems. Like postulates of quantum mechanics, the first postulate say the quantum state of a system is given by a vector in a complex Hilbert space and so on and so forth. Whereas if you open a book of general relativity, you will find that it talks about events. And there's a difference between the two because events are finite in space and time. Can you please close the door, please? Or tell the people to take one. Whereas systems are at least infinitely extended in time, they might be finite or infinite in space. So basically, our two theories start from different starting points. And I think that's the main reason why it's so difficult to match the two. One of the two things may be considered as more fundamental than the other. I don't know. What do you think? So we can have two different approaches to quantizing GR. And one is to take systems as more fundamental, and then GR is made of quantum fields, or the other is take events as more fundamental. Of course, if systems are more fundamental, events are a derived notion. It's something that happens to a system. If events are more fundamental, then systems are a derived notion, like a succession of events, just like it happens in GR usually. Okay, quantum gravity approaches up to now, I think, without any exception, are exploring the first possibility, like take systems as more fundamental, start from textbook quantum mechanics. What we are going to do is to explore the alternative. And of course, we start with special relativity. GR is too complicated. And so what's the problem? In another way of stating the same problem is that textbook quantum mechanics uses time conditioned quantities. Like in the Schrödinger picture, the state of the system is psi given that time is t, so it's a time conditioned thing. Whereas in the Heisenberg picture, it's the observables that are time conditioned. And of course, if you have something that is time conditioned, this cannot be relativistically covariant, you need to start from a foliation in order to even write the states and the observables of your theory. And so, of course, QFT is a covariant theory, but it needs to use a couple of tricks to recover covariances. The first trick is to use observables, to use Heisenberg picture, for instance, which is weird because Heisenberg picture and Schrödinger picture should be equivalent, but you need to use the Heisenberg picture in order to get a covariance, and to use state observables that have a specific time dependence. And then you need to use a state which is invariant for Lorentz transformations, for example, the vacuum typically. Now, we want to do something different. Our approach is called geometric event-based quantum mechanics. It's clear why it's called event-based quantum mechanics, because indeed we take quantum events as fundamental. And quantum systems are derived, a derived notion like a quantum state for a succession of events in quantum spacetime. So how do you define a quantum event? It starts from the realization that an event has a position in spacetime, not a position in space like a system, but a position in space-time, because there's a time at which the event happens. Not only has a position, but it also has some energy and some momentum. There's no energy and no momentum, you cannot have, nothing can happen. So you start from introducing axiomatically a spacetime. This bar means it's a 4-vector. Axiomatically, you introduce a spacetime position. X0 is a time operator, which tells you at what time the event happens. And the rest are just position operators, which tells you where the event happens. Same thing for P mu is the energy momentum vector. And then to quantize this, you just use canonical quantization. You put Minkowski matrix here just because you want to have the Poincare algebra, and you want X mu and P nu to be 4 vectors. So you need that matrix there, that Minkowski matrix. Okay, once you have that, you have the eigenstate X or the eigenstate P. The bar denotes a 4-vector. These are eigenstates of the 4-position operator, of the 4-momentum operator. And then you can introduce a wave function. So this is a probability amplitude that the event happens at some space-time location, and this is the probability amplitude that the event has some energy momentum. And of course, this means not all possible states are physical. We'll get back to that. For example, this eigenstate of the position operator is not a physical state because it describes an event that just happens in a certain location and then everything goes away. So physical states are the ones that satisfy some constraints. I'll get back to that. But you see that you have probability amplitudes, and they are connected. This wave function and this wave function is just connected by a Fourier transform in the 4 in space-time. And the Born rule is just, as usual, the square modulus of the probability amplitude. And this tells you the probability that the event happens at space-time location x bar. And notice that this is an unconditioned probability that the event happens at that location. Why am I emphasizing the unconditioned fact? Because if you look at textbook quantum mechanics, the Born rule is really gives you a conditional probability condition on time. So it's a probability that you find a system at position x given that time is t. So it's a condition probability that you will not find in textbook, but if you think about it, it's pretty clear that it's a conditional probability. So if you start from textbook quantum mechanics, the Born rule quantum mechanical probabilities are not covariant. You need a foliation because it's a conditional probability condition on time. Whereas in this new construction, we are proposing this Jeb construction, the probabilities are unconditioned, so you can indeed define it in a covariant fashion. So the reason why it's called event-based quantum mechanics is because it starts from events. The reason it's called geometric is because in this construction, the Lorentz transformations like boosts are really described. I don't have time to show it, but are described like unitary operators acting on these Jeb states, just like you would expect from Wigner's theorem. Wigner's theorem tells you that the symmetries of a theory should be described by a unitary operator acting on the state, on the quantum state. This is not what happens in quantum field theory, but this happens in this framework here. Okay, up to now, I've shown you what happens to a space-time constructed by in which you have a single event, a single probability amplitude of having some event. If you have multiple events, you can use tensor products, and notice that, or even you can escalate to Fock space, and notice that each event has a different time, because this is the probability amplitude of the event one happening at this location, and the event joint probability amplitude of all the events happening at these space-time locations, and which means that each event has its own time, okay? Dirac had a similar expression, but of course he ran into trouble when he did not know how to describe the fact that these kinds of states have n different times. But in our construction, this is pretty clear. As I was saying, you can either use tensor products in order to describe multiple events, or you can use Fock space. And if you use Fock space, depending on whether you have commutators or anti-commutators, you can describe bosonic events, which give rise to bosons, or fermionic events, which give rise to fermions. Okay, I don't have time to show, but in our paper, you can find that this construction is indeed, this is what indeed happens. Okay, up to now, I've described only the kinematics. Okay, the kinematics of this construction. So how can you introduce the dynamics? The dynamics you introduce by using constraints, constraint equations. So you take the states of your framework, and the states that satisfy some constraints, like the Wheeler-DeWitt, for example, are physical states in which describe the whole history of your system. For example, this is a Klein-Gordon constraint you can write, and a similar one for the Dirac constraint. Okay, so one thing I want to emphasize is that I'm not, of course, claiming that quantum field theory is incorrect. That would be a crazy claim. Of course, quantum field theory is correct. This construction is just an alternative way, in a sense, a different way to obtain the same results. And you would say, why do you want to do that? Well, maybe I want to get a better ontology, a better metaphysics, or maybe this construction can lead us further than what quantum field theory can go. For example, this aspect I was telling you about, the fact that in this construction, the boosts are unitary operations applied on the states. This is already something very nice. Okay, so I've talked about this JEB, this new approach to relativistic quantum mechanics, which takes quantum events as fundamental entities, and then how you can construct observables, Hilbert spaces, Fock space, bosonic and fermionic things, and how you can introduce the dynamics using constraint. Thank you for your attention. Sorry, this is the paper on which you can find more details about. Thanks. Thank you.
Yeah.
A measurement. Okay, I've shown you how you can construct the Born rule. Okay, and one nice thing that you don't find in QFT is that these states, like the eigenstates of this position, space-time position of observable, these states here, you cannot find them in QFT, because in QFT you're just quantizing the solution of the field equation, of the dynamical equations, and these kind of states do not satisfy any dynamical equation, so you're not going to find it. But here you can find it, and they can describe a measurement apparatus. The update rule. Okay, that is a very complicated situation. So how do you do that? You need to describe the coupling of your event system with an external measurement apparatus. You need to use the von Neumann prescription, and then you can construct this by looking at the memory. Okay, so we've done that for the non-relativistic case. In the relativistic case, you need to work a little bit harder to do that. Okay. Which one? Oh, I don't know. You mean the path integral formulation? Is this what you mean? No. It's not the same. Not at all. Because the path integral formulation. Okay, sure. Right. Thank you.
Thank you for the chance to present this today. Okay. Yeah, so my name is Barbara. I'm a postdoc at Perimeter, and I'm going to tell you about how to derive equations of motion for infinitesimal teleportations. So the motivation for this work came from various directions. I need to speak up. Okay. Can you hear me now? Yeah. So it came from, I read a long time ago this paper by Nelson, where he claimed that we can derive Schrödinger's equation from Brownian motion if we just assume that there's some fundamental Brownian motion with a diffusion constant that's related to h bar. I've also been wondering for a while, why is the kinetic energy term the same in Brownian motion as in Schrödinger's equation? And finally, I'm interested in understanding how we can describe back reaction of space-time. Oops. So this talk can be made much longer. I have to apologize that I won't be able to go into all the details that I normally would. So this talk contains many different ingredients. One of them is port-based teleportation protocol, which is a relatively new teleportation protocol. I also normally talk about physics of random walkers and discuss entanglement in quantum fields vacuum, and of course also interaction with quantum fields. So using all these ingredients, I model equations of motion as arising from teleportations over small distances by using port-based teleportation protocol. And we arrive at an information theoretic interpretation of the Planck constant. If I have time, I'll mention comparison to an ADS-CFT toy model and discuss a little bit the problem of time. So the main idea of this work is the following. So we all know from 20th century that our space-time is permeated by quantum fields. And if we put a piece of matter in, let's say, quantum fields vacuum, we also know that it will interact with the vacuum in its neighborhood. Furthermore, we know that there's a lot of entanglement resource in quantum field vacuum. We know this for example, from the consideration of a scalar field. If we remove the Laplacian operator from the scalar field equation, we see that a scalar field would consist only of 3 harmonic oscillators at each point of space. But once we add the Laplacian, all of these harmonic oscillators become coupled, so that you can think of this as a source of entanglement in the vacuum of a quantum field. So instead of modeling all of the complexity of the entanglement in a quantum field's vacuum, I model entanglement as n shared bell pairs at short distances. So between 2 points, there's n shared bell pairs. And I only care about points that are very close together. So in summary, quantum fields vacuum serves as a source of entanglement. We also have some local interactions between a piece of matter sitting in the vacuum and the vacuum itself. So we have entanglement, we have interactions, we are ready to model motion using port-based teleportation protocol. Port-based teleportation protocol, as I said, it was found relatively recently. The second one is the paper where it's described for the first time, but the first one that I mentioned here is, I call it like the proto version of the port-based teleportation protocol. I'll just quickly go over it. Similarly to the standard protocol, we have an unknown state psi that we are trying to teleport. Alice is trying to teleport it to Bob. Luckily, they have shared entanglement resource. And instead of having only one shared bell pair, like in the standard protocol, in this protocol, they have a lot more. They have n shared bell pairs. What Alice needs to do to teleport the state, she needs to perform a measurement on the unknown state that she's trying to teleport and her half of the entanglement resource. And then she needs to communicate the classical information of which outcome she got. The way the measurement is set up is she can get one of n outcomes. So either, let's say, 1, 2, blah, blah, until the n, number n. So then she communicates this number to Bob. And what's cool about port-based teleportation protocol is Bob doesn't need to perform any unitary correction on his side. So he just needs to pick out a port which corresponds to the number that Alice sent him. So if she got in her measurement result 2, he needs to pick out port 2, and the state that she was trying to teleport will come out through that port. I should just mention that this protocol works perfectly in the asymptotic limit when n is infinity, but is imperfect for any finite n. I will not go into details with the measurement today. I don't have enough time. I just wanted to point out an interesting difference to the standard teleportation protocol. Well, the key point here is that in this teleportation protocol, you don't need to perform a unitary correction on Bob's side. Well, you can do that sometimes also for the standard teleportation protocol, but it works only 1/4 of the time. So that's the second line here. And the reason why it works 1/4 of the time is that if in your measurement you manage to project onto the first bell state, then you don't need to do a unitary correction. Port-based teleportation protocol is set up in such a way that no matter which measurement result you get, you don't need to perform the unitary correction. And the improvement of probability of successful protocol without unitary correction, left or right, just like in port-based teleportation protocol, sometimes you just don't successfully teleport. And so from modeling this massive random Walker motion and matching up the constants with the constants that come from Schrödinger's equation, we find that, and there's some other details going into this, where I'm identifying the physical mass m with the mass of the Walker. We find that there's an information theoretic expression for the reduced Planck constant where it's measuring the amount of entanglement in the vacuum. So h bar should go at something like 1 over n or 1 over some power of n. That depends on the details, which details are of course important, but I was more interested in the general behavior. The idea is h bar goes as 1 over some power of n. And I found it interesting that in various ADS-CFT toy models, they get similar results. They get that what would be h bar as a 1 over n parameter. But the difference between my model and ADS-CFT is that in their theories, they have a mapping from one theory to another, whereas what I have done here is I mapped second quantization physics to first quantization physics. So I was describing something that happens with quantum fields and interactions with quantum fields. I reduce the complexity to what kind of equation of motion arises, and that's where I discovered this relation between h bar and 1 over n behavior. Okay, so just to conclude, I think I'm just in time. I found an expression similar for h bar to toy models in ADS-CFT holography, but with no holography involved, or you can think of it maybe as a different kind of holography, where instead of mapping from theories to theories, you're mapping from second to first quantization. H bar here seems to measure the amount of entanglement between nearby points in vacuum. And I think that's very interesting, because if H bar really has something to do with vacuum of the quantum fields in the background, then we can hope to describe back reaction on space-time, because we can describe as the particle is moving in the quantum field's vacuum, it's not only is it affected by the entanglement of the vacuum, it also affects the entanglement of the vacuum, because it's using up the entanglement resource as it's moving. So that would be a description of the back reaction on space-time. And finally, you've noticed for sure that the equations that are derived in this way are in Wick rotated time. So they look like thermal equations. There are two paths to resolution of this. One is considering quantum random walks that allows us to quantum random walks. I didn't get into details of that, but they can describe quantum motion which retains a coherence, so it doesn't start looking like a thermal equation, but it still has a nice IDDT in it. And of course, we should think about deeper understanding of physics of time, and for that you can check my recent talk on Pearson. That's all. So the way I describe it here is universal, because I have not looked into what happens if I have multiple fields. So I have not looked into that. But here it's, yeah, the idea is that there's a field, and I'm just roughly describing what's going on and deriving what are the consequences of that. Yeah.